Okay, so we can officially start now. Welcome everybody to the Power Management and Thermal Control Micro Conference of the Linux Plumbers Conference 2020. Good to see you. I hope you will enjoy the content that we have for this micro conference. We held this micro conference in last year's, so at least. Okay, so there was a power management and thermal control micro conference last year at the LPC, and we had some nice progress. We've had some nice progress since then. Among other things, we introduced the thermal pressure support to the scheduler. The thermal control framework was improved by improving the notification mechanism that we use to notify user space of thermal events. And also we improved our utilities and CPU power management and other parts of the power management infrastructure. So this is the agenda for today. Sorry for the small font. I was trying to match the longest topic title, right, with the font size. So this is our agenda for today, including breaks. And so the first topic is the energy model evolution possibilities, and the lead speaker will be Łukasz Szuba, and with that I will switch over to his slides, and then I will give Łukasz the presenters.
Thank you, Rafał.
Powers. Yeah. Off you go. The floor is yours.
Thank you. Hello, everyone. My name is Łukasz Szuba. I work for ARM in Power team. Recently, I've done some development for the energy model improvements, and this presentation and hopefully the discussion will be regarding the next possible evolution steps for the energy model. So what is the energy model? So short introduction, the energy model is simply speaking an array which holds values of power and frequency for each OPP. So the length of the array is the length of the OPP table. We have recently, it was merged in 5.9 RC1, we have that structure inside every device struct. And where is it used? We use it in the energy hour scheduler, and we use it for a future prediction. So we are calculating the energy forecasting for the future usage for the CPU cluster. And it's also used for the CPU freak cooling inside the thermal framework. And as you can see in this small picture, it works like a lookup table, roughly speaking, or we just seek for a given frequency and we get the power for that frequency. And that's the model that is used also in the CPU freak cooling. And I'm going to tell you also about the possible evolution of that simple model. The first big point would be to consolidate all the energy calculation or estimation in one place, because currently the EAS has a calculation code stick to the fair.c and the header, and the estimation for the CPU free cooling is inside the thermal framework, and they are two different models. And that would be a good point to move the estimation into the one place and hidden by the EM API. And it would be good that we have more information about the CPU utilization, which we currently don't have in the CPU freak framework. And one of the points that would be for the evolution is to create the model close to the scheduler, so we can fit that model with the utilization information, similar to what is implemented in the schedule deal. And that will allow us to also not duplicate the code in the future, because the energy model is going to be also used in the depth cooling devices, and maybe in different frameworks like Powercap. So we would have a single coherency point for that code, and the model would be more sophisticated than the current one in the CPU freak cooling. And so that would need the extension, and the extension would be to handle a custom function specific for a driver or a platform. So we can exchange the power estimation function, which is based on the utilization from the scheduler, by some real, for instance, power meter, which is associated with the CPU device. Or we can have a driver-specific function for the GPU, and that will be also handled by the energy model and accessible via API, a common API. What's the current situation, for instance, for the CPU freak cooling and the energy model? The current situation it's shown on the picture. We use the energy model to estimate the power budget for our solution, which is the thermal governor intelligent power allocation. And that governor is basically polling the CPU free cooling devices and the thermal zone every, let's say, 100 milliseconds. And based on that, during that polling, we sample the current frequency and we check the idle time, and we get the power for that given frequency from the energy model. So the private energy estimation, which is stick to the CPU freak cooling, it's basically not working fine. And there was a patch set proposed by Viresh to address some of the issues. And I will shortly, in the next slide, give an example of the problem that we actually have reported by some vendor. And so that usage here is required for estimating the input power for our solution for the thermal governor. And to calculate the input power, we need the current frequency. Then we pick the related power for that frequency. We scale linearly by the busy time. Actually, this is the information that we need is the idle time. And based on that, we calculate the input power for our solution, and we get the output power for the next period. And this is the issue on the next slide. So for instance, the sampling, I call this sampling, every 100 milliseconds, the governor is woken up and it checks the current frequency. On that plot, you can see the red line is the current frequency for the CPU, and it's driven by the schedutil. And due to the fact that it's schedutil and schedutil always go to max frequency for RT tasks, we can have this kind of situation when the RT task is going to sleep. So the frequency is dropped on that CPU, and accidentally we get the sampling at that time, and we get the lower frequency than it was in the past. Most of the busy time was occupied by the highest frequency possible. This is the maximum allowed frequency, that dotted line, which was capped by the governor for that last period. And we, based on that sampling, if you remember the first slide, we pick the corresponding power, which is lower than the real power was used. And then we feed that wrong information to the IPA, and the governor, just after the sampling, it sets the maximum capping not to the right frequency. Maybe the allowed frequency would be a bit higher, but unfortunately, due to the wrong estimation, we got this issue. It's present mostly on the RT task. I couldn't repeat that situation with the CFS tasks. And this is also because of the model which is in there in the CPU freak. It would be good if we have something like that. So when the governor...
Quick question.
Yes?
If you could clarify. So say you didn't have that problem and the sampling was lucky. Do you account for the different energy in different idle states, or only for different frequency states?
So the model is really, really simple. Let me go back. We just blindly assume that the current frequency was the constant frequency in the past, the whole period. And we also treat that the idle time was basically one idle state. We don't distinguish idle states at all. It's really only a scaling by the busy time versus total time based on that information. And we scale that value. So we
Fair
scale
enough.
that power.
Okay.
Which
Thank you. You answered my question.
Okay, I had the same question on that, and I was wondering, if you choose not to have a more complex model, then maybe we should at least limit what we consider as idle to the states where power is collapsed. Because the thermal, at least, its voltage has a way bigger impact than frequency.
Yes, so the idle time is also a good point. We don't track each idle states, and we don't model them. We just simply get the busy time versus total time thanks to the idle time that is tracked. But so that would be that could be implemented via this driver or framework specific callback. If someone knows, some platform knows how to better estimate or even to get the real power from the real power meter, which is pre-programmed for, let's say, 100 milliseconds to do the average, then there is no such problem, because that covers every idle state or every frequency change if you have the real power meter. Or if you have a platform which will just register the more sophisticated callback to estimate the power for that device, then also it's not probably a problem. So that's the possible evolution for the energy model. So not only work as a lookup table, but give the user an option to register its callback function, which might be called via EM get power API. And then in default for the CPUs, we can provide something like that, the estimation based on the CPU utilization, and then we pick the closest possible frequency based on the average utilization from the energy model, and we return that estimation up to the governor or to some other framework other than thermal, let's say Powercap. So that's why I presented this interface as being more flexible and not try to code but platform-specific approach, track idle states or some standby modes or something like that for CPU devices, or maybe so for even a GPU or other devices. Because for the GPU we even don't know, it's driver specific basically. So if there is a device, because we have to control also other devices like GPU, which takes quite significant amount of power, then that interface is more flexible.
I have a question here.
Yes?
I have a question here. So when you have a driver-specific callback, what's your input? What are you asking from driver? Like I can understand for CPU freak, I know the frequency and other, but for for example, some other device.
So yes, so currently in the mainline there is a solution for dev freak devices. It uses the callback called get real power, and the input is the maximum voltage and the frequency which was allowed for the last period. So we can say that we have a cap state. So we provide as an argument, this was the maximum possible state for you. So you can use it for your private calculation, that was the limit. And if you have, or even it was the maximum state, you can treat that as a maximum state and give me the power. So that would allow you to read the voltage and the frequency for that maximum state if you need this, because currently in DevFreak it's explicitly sent the voltage and freq for that interface get real power.
But for even that is true for even like GPU, same thing, frequency and voltage.
Yes. Yes. So that's basically the idea that was requested by our GPU guys in ARM. So that interface, that new interface was coded for that purpose.
Can it be more generic, like
and in here
power?
We can just simply abstract that as a maximum allowed state for the device for the last period and use it locally for your calculation.
Okay.
If it's a power meter, then there is no need to have that knowledge about the max cap state, because you just simply have the pre-programmed power meter or something like that, and you just read out the value. But for some other models,
yeah, that's where I was going. So for the power meter, if I have a power meter, I can directly just pull it from then, give it to the whatever API, right?
Yes. But if you have a model which is, for instance, a kind of polynomial model, which you try to take into account idle states that you tracked locally, and you need that max state, because you need to have the maximum allowed power, and then you scale that value by some model that you have, and it's not linear, then you start basically from that point, from the maximum power, and then you scale it linearly or exponentially, whatever you want. But you need the starting point.
Thank you.
So this is my last slide. I hope for a kind of a discussion, especially regarding this kind of feature, because for the CPUs, we could try to estimate and write some generic function for the CPUs. For other devices, we basically don't have such information as utilization. Maybe a DevFreak framework could provide a specific callback if it tracks utilization, because it tracks busy time and total time. But for the CPUs, if we code some function close to the schedule util, like we have the compute power inside the EAS in the fair.c, we could try to estimate the power value for the last period. We had some internal discussions during the review of my internal code and during the dry runs that, for instance, the utilization of the CPU might not be aligned with what we need. It's not 100 milliseconds. It might be shorter. So this raises some question, but I pointed out that there is a thermal signal which tracks privately in a paired-like configurable decay period that was merged quite recently, which was coded by Tara, if I recall correctly. And I thought that might be something similar could be tracked locally in the energy model for different periods, whatever is the need, let's say 100 or 60 milliseconds. Or
Lucas, I have a question for you. So
yes?
For the energy model, are you more interested to estimate what was the previous power consumption, or what will be the next power consumption?
Yeah, so
for me,
this is the main...
complete, yeah.
Yeah, this is completely different because current functions, they are for the prediction. So they add this 25% margin due to the function map util frec. But we are interested in the real value. We are not interested in the prediction. So we cannot reuse the existing function. We can reuse some code, let's say the scheduled utilization, how it's calculated. But we cannot just simply call the EM CPU energy because of that future prediction which is in there.
Okay, so that's really about how much power have been consumed during the last period, and not how much power we expect to consume during the next period. Because for the ES, it's more about the prediction. The ES is using the energy model at scheduled right now. But what they are interested is about what will be consumed next, more than what have been consumed. In your case, for the thermal, you're saying that you're interested by what have been consumed more than what will be. I don't know if it's really about what have been. I mean, when you're thermal, if you know the temp of your junction, for example, what you're interested is how much power you consume and how this will impact this junction temperature more than how much you have consumed, because I would say that you already have that thanks to the temp.
We have in our IPA algorithm, we used actually the data from the past to predict the future, yeah. And it's simply a PID algorithm. So yeah. It's a quite old idea.
Yeah, I agree, but I wonder if we should more focus on the prediction of the power consumption for the next period more than just trying to compute what have been consumed. I don't know. Because my point is that the way you're computing that and what you are interested in is a bit different.
Yes, but so it would be the second interface, because the current existing one is actually in the prediction, but the new one, the possible new one, would be about the past. So you would have the prediction or the past. Well.
So that will be a new interface. I saw that your goal was to have one interface with the energy model. Okay.
No, you can have you will have both.
Okay.
Question here.
Yes.
So I'm not sure how the knowledge about the utilization helps you if you know the frequency already, given that the schedule governor is used, because the schedule frequency is proportional to the utilization. So you already have this information rescaled, but that doesn't matter. But this is so what's the difference? Like, what do you need the real utilization for?
So I would need the same utilization actually that scheduled has, the average from this run queues that it's going to sum up because of that jump. So to avoid the sampling problem here, if I have some signal which will be slowly decaying, then I would say, okay, the average frequency wasn't that sampling frequency, was actually a bit higher. Then I pick up from the model a bit higher value. So let's say we have the corner case when I sampled that frequency, but actually I've been running at the maximum. And from the average, it's showing also you are close to the maximum. So maybe pick that one from the utilization. And that will help me to estimate the real power for the last period.
You will have to take care because in SchedUtil, you have the raw utilization signal, but then on top of that, we have utilize, which can impact that. And then we have uclamp, which means that at the end, from a SchedUtil point of view, the utilization that is provided can be quite different from the real utilization. So for your power model, you will have a huge difference. You would probably need to use the raw value of the util average, the one before being, I would say, overestimated for RT and so on.
Okay, thank you. I make some notes.
So we already have exactly that for the EAS stuff. Okay. There's one callback in SchedUtil that just computes the sum of the util averages and things like that. And then there's another one which includes things like uclamp and all that stuff. And that's how we compute the busy time. So yeah, I suspect you want the same thing.
Lucas, so kind of going back to the idle, is there any provision for treating idle differently, even if you don't have the additional information? Daniel was saying something about scaling idle to account for dynamic power, but I was more talking about the fact that some idle states will not have any dynamic power because they'll be completely turned off, or they wouldn't even have any leakage power because they're completely turned off. But some idle states will still have a lot of leakage power because they're just clock gated. So can we at the minimum introduce like a flag saying if it's kind of below this level, consider it idle. If it's above this level, don't consider it idle. Is it something we can do?
Yeah, that's a tough question. And we also, in EAS, we don't track the idle states at all, or idle costs. And that would be a really tough issue for us to tackle.
Yeah, that's kind of why I'm bringing it up, because it's not sufficient to just work with SchedUtil or scheduler directly and just know idle or not. Because having worked on thermal issues myself on products, clock gating versus power gated makes a huge difference in thermal. I'm pretty sure most of you guys know that already. So not taking into account seems like not really trying to solve the problem.
We need to wrap up this topic because we are going to go over time otherwise. So thanks Łukasz. Thanks, that was interesting. I think that we can continue on the mailing list. Unfortunately, we are the last MC in the whole conference, so there is no time for buffs left after us. So we need to continue on the mailing list. So thank you.
Thank you, everyone.
Daniel, it's kind of, I'm assuming that you can take a presenter yourself and continue.
Okay, can you hear me? Yeah.
Yes, all is fine.
Okay, so my name is Daniel Escano. I'm working for Linaro. So 2 years ago, we talked about the thermal zone hierarchy, and well, there was not a clear consensus on this approach, and that had to mature a bit. So I'm coming with a new proposal. So the main goal is to be able to distribute the power among the different IP we have on the SOC, and based on the central logic. So in order to do that, to have this temperature and skin temperature to be mitigated from this logic, we have in user space, this is the current solution. We have the thermal framework, which is doing mitigation action to protect the device, preventing getting too hot. And in user space, we have some kind of thermal daemon, which is So I'm talking about out of 3 solutions we have today. So that's the way vendors are trying to deal with the skin temperature. So they are constantly reading all the temperature of all the thermal zone. So as a reminder, we can have up to 20 or 30 sensors now on the SOCs, and they are polling that. And from there, they change the state of the cooling devices directly, hacking the cooling state, the cooling device with opaque values. And there we have a conflicting decision between what we have with the thermal zone, and which is doing mitigation action, and we have a thermal daemon acting directly on the cooling device doing power capping action. So the proposal is, instead of having that, is to provide to the user space another component based on the power capping framework existing today to act on the power on the different devices using the energy model. So instead of having this thermal daemon touching here and there the different knobs you can find everywhere on the surface, in the brightness of the screen, on the CPU frag, on whatever, we provide a single place where I can use the same unit, which is the power, and set the power on the different devices. And thanks to the design of the Powercap framework, we can create an hierarchy of constraints. Like that's an example. Does not especially reflect an hierarchy of the hotspots or the thermal zone. It reflects an hierarchy of constraints. And thanks to this hierarchy, we can, for example, set the power limit on the CPU here in this node. So in this hierarchy, only the leaves are the real performance domain we can act on. And the intermediate node, like the CPU here, is a virtual node aggregating the information of the children. And in this case, for example, the CPU here, the maximum power we can have in this CPU is the sum of the maximum power of all the children. So if we set a power limit in this at this level, then we can have a logic to mitigate, to distribute the power among the different child. And so in this case, for example, if the first performance domain is not taking the entire power of allocated power to the parent, the CPU, then we can give the free power to the other CPU. And if the first one is wanting more power, still under its power limit, we can take the power back from the first one to the second one to the first one. So we can do some balance in the power based on the power limit we put in the parent. And always we make sure that the constraint is fulfilled by setting the maximum power on the CPU, which is the sum of the power consumed by the children. Also, we can do something more complex, so we can set the power limit at the package level, and then automatically we have a distribution of the power around the different children, which is using recursively the tree hierarchy to distribute this power among the children. And if we want to create a dedicated bandwidth, we can create a new power limit on after setting a power limit we put on the parent to dedicate a power on a specific node. So the balance of the power will occur only on the other one and not in this one. And this approach, we don't have to force to have the incarnate logic involved in the power distribution. We can also let user space handle that directly. And for that, the user space can just set manually the power limit on each node. he wants to do power capping on. So these are a few use cases we have with this approach. So that can be used to clamp the power, to limit the power in some scenarios, like for example, when you are running a web browser and you don't necessarily need to go to the highest OPP. With the today, you take a web page, you load it, and automatically we go to the highest OPP while it renders the web page. And if you use the OPP just below in the previous one, you will have just a slowdown of a few milliseconds for a huge amount of power saving in this case. So when you catch this kind of scenario, you can limit the power on the CPU because you know that the performance won't impact the user experience. Also, we provide a unified interface where we can act on the power on the different devices. And it's a way also to provide a solution to all the out-of-tree kernels we have around, and that will allow decreasing the fragmentation we can find in different SOC vendors. This solution allows to have a in-kernel logic. Sorry, I forgot to put the phone in mute.
Can I ask you a question?
Yes.
So like, we are, like recently I did similar change for thermal D which has awareness more about the context. How do you know that web browser is running, for example? How do you decide that, do you pre-program? Do you know before that these are the programs?
Yes, you have a hook with Android. The different applications are classified, and you have top application, and when it is able to catch this kind of application is running, and then apply a hook and call some callbacks to do some setup based on that.
Yeah, I'm looking for some more generic where, like if we can classify sustained versus busy, and those some heuristics in the kernel tells me that I'm sustained or busy or one short, or it would be great. Yeah, because this is a lot of hand tuning, right? Because in Android you can do that probably.
Yeah, I think so. Yeah. So this framework, this Powercap framework, allows also to, as I showed right before, we can have a full in-kernel logic for. I'm not sure it won't be very complex if we want to put that on the root node of the hierarchy, but at least for some group like GPU, CPU, or big little, that could make sense. We allow also to have control from user space only, or we can make both. So we can set the power limit on different nodes and set a power limit on a parent to let the children to be managed by the in-kernel logic. And because there are an infinite number of constraints we can create with the Powercap, so we can continue extending the feature of the Powercap hierarchy by defining different semantic for each constraint. For example, allowing to go beyond the power budget during an amount of time, like a turbo mode, something like that, or whatever we want. We can use this existing framework to extend that. Because we have in the in user space, in the kernel space, we have the different notification. We have all the information. We can get synchronously the information about the changes in the performance state of the devices. I think it's reasonable to say that probably we will have a better reactivity to mitigate the power, or to limit the power, rather than relying on the temperature and changing the states. Okay, so that's the proposal. I already sent the patch set. I had no review. That was just before the vacation, so I'm sure everyone saw it. I sent the patch set to act on the CPU power based on the energy model. So of course that is based on the energy model, ARM energy model, and the power management framework. So both plus the Powercap should be able to create this hierarchy and provide a solution for the different sub vendors to limit the power of the different devices.
All right. So what exactly is the difference between this new framework and the existing one? So still to control temperature, you still need something like a thermal daemon, right? That will read the temperature. Or do you want the kernel to control the temperature?
No.
And then okay.
No, for the moment the step it's too big. I'm not sure. I don't see a need for that for doing that now. What I see, it's what is missing is an interface. To act on the power on the different devices. Today, the different thermal engine are acting on the cooling devices states with opaque values, and they are doing some experimentation and make sure that is letting keeping the temperature above the desired temperature to decide in their database or whatever.
So currently, right? If you, for example, you have sorry, Rafael, you go ahead. Sorry.
No. That's fine. I just go ahead. No problem.
Yeah. So currently, like, suppose you have 5-6 devices, right? And they all, with the Powercap current API, you will see all those devices already in your sysfs. And if you have some energy model in your in daemon, you can do everything what you said, right? You can distribute power, you can take an advanced action. So what else we need to add in that framework?
The backend.
So backend for each driver.
Yes, so today we have the RAPL backend for the Powercap framework, but we don't have the backend for the ARM with the energy model.
Oh, okay. See, so that has to be added for per, in your case, like each device. Okay.
Yes. So Intel has already this interface available via the RAPL register. So
yeah,
it's fine for them. But for the ARM architecture, they have nothing to act on the power directly.
So so you will put that energy model, whatever energy, data structure in the Powercap framework, or it will be per driver framework, right? They have to register probably energy model with your Powercap framework, right, for each device. So yes, so the versus power, right?
So yeah, so Lucas did some changes recently, and we moved the energy model structure inside the struct device. So potentially, this if the different drivers fill the energy model array information, we can potentially have the power numbers for the different devices. Of course, that won't happen in one day, but for CPUs and for some other, for CPUs and GPUs, at least we can put this these interfaces in the Powercap.
Daniel, what about this setup interface? How to create this hierarchy, the package and the GPU, memory, CPU that we presented? would it be
So
possible to?
That's a good question, and it's still we are still thinking about that. So the first idea is to tie the different. Well, we have the different power domains. We can put the generic power domain. We can put the device in, and then we can create a Powercap entry trying to group these different power domain and describing this hierarchy. That's that will be one solution. The other solution, I don't know. For the other solution, I don't know if we can act on the sysfs hierarchy directly or not. Not sure.
Question in the CPU case. Say you want to have use this for the CPU power capping as in your patch. So do you, and you have the EM for CPUs right now, right? So what do you use as the additional information that allows you to figure out what power was? Like, do you use the utilization or do you use other signals?
So yes, so that was the reason why I asked Lucas' presentation to be before this one. Because,
I see. Okay.
Because right now it's very simplistic. So when you get the power, you don't scale that with the real usage of the device. We just use the current power used by the state. It is the OPP. It is running on. But the idea is make something more fine grained and use a power meter Lucas was talking about before, where we scale the power usage on the CPU with the utilization.
So the utilization could be used for this purpose, right?
Yes, right. But we don't want to duplicate the feature for everything. So we know that we need this get power thing in the energy model for the cooling device, and that could be reused by the Powercap.
Okay, or the other way around. Actually, you could share this information, right, in the two places.
Right.
Well, possibly. Okay. Any more questions for this topic? Comments? Anything?
Yes, I see a question from Lina. Oh, sorry.
Oh, go ahead, Daniel.
Okay, so I'm seeing a question from Lina who asks, would you merge IPA into the Powercap framework? So I'm not sure. It's not. Somehow it will make sense to reuse the share the information and the API to act on the power, but I'm not sure it makes sense to merge the IPA with the Powercap framework yet.
Yeah, currently there are no such plans, and the thermal is slightly different than the Powercap, and the IPA is actually so that in thermal we have actually only one thermal zone and IPA, because IPA doesn't work with hierarchical thermal zones, so it's different and limited, I would say.
Right, correct. And the governor are aiming to protect the silicon, while when you want to do power limitation on power capping, you act proactively to prevent to go some temperature or to reduce the power consumption or to do some power budget. Okay.
Okay, thanks.
All right.
Okay,
I will ask on the list. No.
Sure. So we still have a couple of minutes, but let me. So, is there anything else, like a short question, that we could still accommodate?
So I have one short question.
Okay.
Because the current thermal doesn't take into account the possible power issues with the power rails or something when it allows to go at max frequency for every device. It's not ready for kind of a turbo OPP, which is like for one core only. Do you think, Daniel, some other features might be monitored as well in the Powercap? Because the thermal only monitors the temperature and that's it of the device. Not, for instance, the maximum power drain at current moment.
That could have, I think those kind of scenarios, I think in previous LPCs we discussed, like either dependency of thermal zones are not there, right? And you need to create a dependency. Currently, they are independently acting. So really, if you need to act on the multiple devices, in this case, I think you need a dependency, like you are talking hierarchy or whatever dependency you need to create, right?
Right.
And that's the part missing.
It's actually worse than that, okay? Because there's no power delivery constraints as well. You can have current limits, you can have power limits completely independent of temperature.
Yes, exactly. And currently in the thermal, we don't model that stuff. So is it Daniel, also in scope for the Powercap?
No, not for the moment. I think now the first step is to create something simple and unified API to access on the power of some devices. For the moment, that's all. I think it's the first step is to do that, and then I have a logic. I have wrote some algorithm to do some balance across two devices. I would like to validate first, but for the very first step, I think it's very complicated to do that in as a big project. We need to do that iteratively. And I think the main goal today is to provide unified API to act on the power for the ARM platforms.
Thank you. I think that we need to wrap up at this point and then switch over to the next topic. This was interesting. There is one thing I forgot about, which is the shared notes. I didn't ask anyone to take them. I was trying to take notes for the Daniel's topic. They are mostly missing for the first one. So if anyone can help to fill the gap in there, I will be grateful. Also, if you can take notes for the upcoming topics, because I'm going to be involved a bit in them, and I'm not sure if I can do those two things at the same time. I will be grateful as well. The shared notes button is on the left-hand side over the list of participants. So anyone can do that, as far as I can say.
Thank you.
Okay, so let me take the presenter now, and I will switch over to the Srinivas's slides and then give a presenter to him.
So doesn't any button comes that I'm a presenter and I can move slides?
There will be.
It's like
going. Okay, Srinivas. Yeah,
so how do I
make
move
you? I need to make you a presenter. Let me do that. Now you are the presenter and you control.
Oh, okay, there is something. Okay.
This is this the right deck?
Yes, it's correct. Yeah.
Did right? Okay, great.
How do I move to next slide? There is some button. Oh, slide. No. Okay, there is one. Okay, I see that. Yeah. So you can start now, or?
Yes, please. The floor is yours.
Okay. So my name is Srinivas Pendruwada, and I work for Intel. And maybe the first two presentations were for very, like mobile devices. But what I'm going to talk about is very big servers. So there's a big switch. So to give a little background, we have support of Intel Speed Select technology from last less than a year, and particularly targeting servers like ICX with lots of cores. And it has many features. So there are 4 features, but one of the feature is called performance profile. And what this feature does is basically allows the users to dynamically increase the TDP. And if you can keep specific cores in C6. So the motivation is, we have these servers with like, tens of cores, like 26 cores in ICX. And not every workload really reads those many cores, and it doesn't really scale. But most of particularly the older workloads, or some high performance HPC type workloads wants very few cores, but very high guaranteed frequency on those cores. And we submitted to upstream for more than almost a year now. And currently the model is driven in the 2-step approach. It's a user is in control. We have driver. You say that, okay, now I want to switch to higher TDP or lower TDP. Like we have it currently, there are at least 4 levels. And then we know before that he knows based on the profile which specific cores needs to be in C6, which can be active. And the problem is we have to trust the user that he does the correct action. And that's where the problem is, and the trust factor. But we can all drive this from our firmware, so we don't really need the user intervention this much. But that's the current model. So that's why we are exploring how to even use the hardware to drive all these things. And this is not there.
So can you clarify a bit? Is it like the user has to offline and the right number of CPUs manually for this to work? Okay.
Yeah. And so we are exploring the use of hardware to assist in this process. And it is not there, but we want to bring it in this feature. So we want to get some feedback on how do we implement that. We can have hardware can implement it, but we cannot do it, then it's not much useful.
So the goal, I guess, will be for the firmware to kind of tell the kernel which CPUs need to be put into C6, and then the kernel will do something to make that happen, right?
Yeah. Yes. So though we have this something called Intel hardware feedback interface, and some of my colleagues are working to upstream this feature. So we want to, it'll be very similar to utilize, but that was currently it's getting supported in very client devices, but we want to make it more generic. And what this hardware feedback interface is, we have, the kernel will provide a memory location to hardware, and hardware fill it the information like, for each CPU's, what's the performance and what's the efficiency and those numbers, and they can change dynamically. And whenever the hardware will change, it will send you a thermal interrupt. You can go and read the whole table at one time and take action. And there is one specific value here is called performance equal to 0. So what does it mean is that don't schedule anything on that CPU. Basically, just get away from it. And we want to utilize.
What are we going to do with CPU affinity?
Sorry?
What are we going to do with CPU affinity?
Yes, yeah, okay. I'll go through that in the next. I have that topic too. Yeah, I'll go. So currently, the way we do it is. So currently, when user space does online, offline, the affinitized tasks also move, right? It doesn't stick there. If so, it's not really like, keeping
But
that.
it's destructive. Offline destroys information.
Yes, offline destroys information. Yes,
Yeah,
that's correct.
We're not using offline. Hold your horses.
So there are multiple thinking. How do we implement that? Simplest, we thought, okay, let's use performance equal to, when equal to 0 means, okay, I'll just remove that CPU from the CPU set. These calls are already there in kernel and people are already using it. But the big problem with this approach is, the CPU 0, online, offline, is a big problem. And most of the time it works for me in the lab, but somebody sends me report, something CPU 0, it failed to offline. And then the whole model falls apart. And that's why it is, it's not really a preferred model. In addition to, like Peter, you're saying, it will break your affinity, right? Somebody really wants to run on some CPUs, you really move you out. So not great option. The other option we thought of using idle injection. And first of all, the current idle injection is primarily targeted for thermal type cases. It's like, you will be there for some time and will come out. But in this case, the servers will stay there for forever, probably, maybe for very long, till somebody's paying for it. And then once he's out, then, he will change the profile to somebody else. But so currently this framework really doesn't allow you to set the runtime to 0, and which is fine, because we really don't target 100% idle. But I did a lot of experiments to use that framework to be in around 95% plus in the C6. But then I see lots of warnings and errors popped up in the D message, particularly with the networking device who has that their watchdog, internal watchdog. If they something don't get serviced in certain time, they start their watchdog and you break your link. And in addition, I see lots of error with unstable TSC become unstable because the RT task, maybe, I don't know what, it kept it so busy that nothing can work. And so also affect the soft argue. So it's not really, I couldn't make this work with idle injection without errors and to meet the 95% C6 case. So the next choice we have is, use this CPU capacity, right? And as I said before, we will be having upstream support maybe sooner, not because of server, but because of clients, where we will use this capacity, dynamic capacity, to use, in the scheduling decision. But there is a problem here. The problem is, like, when I tried that approach. So when we map performance equal to 0 to capacity equal to 0, it really doesn't matter, because when the overloaded case, we can and servers, you will see many processes. Most of the time, it's not going to be idle, because some people are paid a lot of money, so they want to utilize everything out of it. So capacity 0 falls apart, because whenever there is an overloaded case, it will schedule on those CPUs. Like, for example, in this case, I don't want to schedule anything on the core 1 or core 2, which has 2 siblings, both 2 and 6 here case. But still, it will schedule. So what we really want is something like this. So it is fine that sometimes like a 5% utilized per interrupts or any RT type things, and most of the people who really runs fair normal type things, we want them to be totally as far as idle, like maybe 95% busy, but idle and rest maybe can be busy. So this is what we want to achieve, and this is what I wanted to I tried to experiment. And I was able to achieve this. Basically, I used very special. The capacity 0 currently is basically changed to 1. It's not really special. I wanted to make it special that on all these paths, wherever we select a CPU to run, like in the wake up path or load balance or idle balance, I treat the capacity as very special, 0. zero capacity as special, and I don't select it select. So any of the fair tasks, CFS tasks will never be scheduled on this. And this was able to, at least I was able to, with my experiments, I was able to keep the cores into C6 at least 95% time, even with different, server workloads which people run. Of course, if someone wants to really run, RT task or something, or affinitize, they can still run it, because if someone sets an affinity to those CPUs, yeah, it will still run. And so that is the difference between. So if someone wants to do task set, they will still run RT tasks, and anything busy task, those they want to keep it running, they will still run. And as Peter was saying, the CPU offline actually is not really great, because it breaks somebody's affinity. It's a destructive, right? So we don't. It's so ideally we want to use capacity equal to 0. And and the question is it really a problem? Is it like I'm thinking is that maybe the capacity equal to 0, maybe special case in ARM platforms. Maybe it's not, which is you are using already, that you cannot change the behavior.
I have a question for you. Instead of using a plug, have you tried to rebuild the skid domain to put those CPU in a dedicated skid domain without a load balance between this domain and the other one? I mean, to make them as an exclusive. So everything that is pinned to them will continue to work, but normally you will not migrate anything on this group of CPU. You save this unplug and plug things. You still have the cost of rebuilding the skid domain, but if this has to run long enough, that should not be a main problem. And I mean, you can put the only things that you will have to set explicitly a CPU running on this group of CPU, which it seems that can happen.
So so basically you're saying that user has to create a different CPU skid domain, or is it like you're talking a little, or I can create in the special domain in the kernel code?
So the C group, it's the user space interface to create such group of CPU. Yeah. But at the end, the C group are going through the kernel. So I'm not sure that there is anything available
inside kernel.
Yeah, that we can trigger, but I mean, I don't know. Maybe that will be a bit nicer than trying to bias the capacity of the CPU. I'm afraid that with the capacity equals 0, you will create a lot of special use case.
I only saw 3 places. It's not really a lot of places, because it's already pretty abstracted. But if I do create domain in the kernel bytes, without user, so the user, I don't know how the interaction with the user he will see, because I created a CPU C groups out inside kernel without user's knowledge.
Yeah.
That is something I don't know whether those customers will like it. So I need to think about it. That's one suggestion. So I'll play with it and go work around, see that how that is taken with some of our customers.
So Srinivas, if you do have a real-time task or some other pin task on that CPU that continues to run, how will the hardware react? Will it just not be as efficient, or will it be really, really sad?
No, it will not let you reach your TDP goal. That's the only. It'll let it run. It's not going to stop you. It will cap its performance, but.
Right, but this mechanism will be ineffectual.
Yeah. So you'll lose your TDP what you wanted to achieve if somebody was running it. Then if somebody really wants to run and make sure that no RT, nothing runs on it, he has to really do offline. He doesn't have this.
So this on chat. This is needed for mobile workloads too. So it's definitely not need only for x86.
Can you say that again, Saran? I missed the chat somewhere.
Yeah, they're saying that this is useful for ARM too, for mobile workloads. So it's definitely something mobile workloads want to.
So you think that capacity equal to 0, we can treat it as a don't schedule type thing, right?
I'm not saying that. I'm just saying the goal of what you're trying to do of isolating a CPU, even when it's active, sorry, even when there's a lot of workload, is something that's desirable for mobile too.
Okay.
Not specifically the implementation, but the goal.
Okay. Yeah. So yeah, I'm basically the idea of my presentation. I'm looking for suggestion. One like Vincent said, it's get domain. I never thought about it, so I had to go and look for it, see how we can do that. Any other suggestion?
I mean, the main question is that is there really a fundamental problem with going for capacity equal to 0? Because if there is a fundamental problem, then we have to look for other options, right?
Yes. Yeah.
But if there isn't, then perhaps that is possible. That is a possible way to address this, right? So this is a real question. Is there a real problem with making those changes? But I'm not sure if we can answer this during this call, right? So perhaps it would be necessary to send a patch and see what people think, right?
Sure. I will send it. So so Peter, you don't see fundamentally. You don't see from very 100 1,000 feet level. You don't see big problem with at least going this way, right? Before I spend a lot of time.
No, I mean, it's hideous, but I think it should work.
Mm-hmm. Okay.
Hi. Won't it break a lot of the tracking we do at group level, just ignoring some of the CPUs in specific data paths? I think Vincent's idea with actually removing it from the get domain hierarchy should help you with that. So I think just hacking in that you avoid CPUs with a capacity of 0. I mean, I wonder how many things we track in the scheduler that will break by just doing that, because you have a group of n CPUs, but effectively you decrease that number by the number of CPUs where you have set the capacity to 0. But for all the tracking purposes in the scheduler, it still thinks that there are n CPUs in there. So I'm wondering if load balancing can be messed up and group scheduling and other things.
But when you have capacity equal to 1, you are already you're already taking care of the right capacity field, right, in your balancing decision, right?
Yeah, for the places where we use the capacity, but if you use the number of CPUs for anything in any of the calculations, you don't remember if we still do that. But
there might be corner cases we don't know about yet.
Yeah, and so I guess the point is that there is a whole I mean, how to say, statistics and other things like that depend on this somehow, right? That can be broken, like reporting, not just the functionality, but also reporting that can that can confuse somebody, because
Yeah, because the scheduler's view is still the schedule domain hierarchy, and that's what it uses for tracking everything, right? And we are effectively removing CPUs here. So I think that the easiest way to try to avoid some of those problems is basically to rip it out of the schedule domain hierarchy. And I'm wondering if that's too expensive to do for your case. I mean, how often do you expect to rip it out and put it back in?
That's
domains is very expensive, but what timescales are we talking about? How often would something like this happen?
Yeah, it's not very quite often. It's in probably one. We are saying that don't do less than minutes. Don't change.
This is something that a user would do. It's unlikely something that would happen in response to real-time events or programmatic events.
So currently it is done by OpenStack stuff. Yeah, OpenStack is doing it. And we tell it's not like in microsecond or millisecond. It's like in minutes. You shouldn't change your profile every 6 seconds. It's not.
So, in this case, rebuilding the schedule domain could be a possible way. I mean, even if it's expensive, if you're in the range of a minute, that's almost nothing.
Well, what happens for a bound CPU if we rebuild the sched domain for a pin task?
It stays there.
It still runs? Okay.
You'd have the same issues in terms of keeping statistics, right? Even if you use a skid domain, if you're looking at average CPU load, suddenly it's going to not look like 100%. So are we really solving stuff by using skid domain, at least in terms of statistics?
Yeah, because when in the load balance, for example, so yeah, I don't know why you will have a problem. We're already supporting a different skid domain. I mean, that's already there.
No, I'm saying functionally it'll work, but the question was, what about statistics and reporting? I'm saying skid domain, I don't see how that will solve that.
About
right?
which statistic especially?
No, just one example I'm just throwing off on the top of my head is like if you're looking at average CPU load, if you have like 4 CPUs and one of them is forced to not run like this, then it's going to look like 75% because it'll be like 3 times 100, 300 by 4 or by 4, it's going to be like 75. So yeah, that's what I'm trying to get at.
Yeah,
right. People that use utilization for capacity are easily confused, and they're going to get confused no matter which way we do this, because they have to be cognizant of this change for those statistics to make sense.
Yeah, so I'm saying I don't see, that's my point. I'm saying skid domain doesn't really make this any better in terms of reporting.
For internal use, it does. I mean, the problem you're talking about is reporting to user space what the utilization is, right? Well, for internal scheduler use, removing it from the skid domain hierarchy is as good as removing it using hotplug, I think.
Okay, yeah, okay. So I need to experiment that and maybe then post the patches based on that. So, only thing I worry is, because CPU sets are used very heavily, and I patch something in the kernel, users may see totally different than something get added behind in the backdoor to him.
I just wanted to add that we don't use capacity ORIC off in all code places. So that means you also have to check for the use on the run queue, so the run queue CPU capacity ORIC. It's not all encapsulated in this function. And since you mentioned capacity equal 1, what we said in the update capacity function, there is a slight difference between capacity and capacity ORIC.
Yes, so what I saw that. So what I also do is whenever there is no, there is a check in the scheduler CPU not active, right? I also put there also. So it's, yeah.
Yeah, another problem with the load balance is that now we are comparing the number of running tasks in a group compared to the number of CPU, whatever their capacity. If you play only with the CPU capacity reach, we'll still see your CPU part of the skid domain, and we'll consider him to be idle. So we'll say that the group is not overloaded, whereas we can't really use it. So that there is a lot of side effect. That's why. Because everything is based on this.
Okay, that's a good suggestion. I need to really experiment that one. Yeah, I don't know much about it. So
okay, so according to the schedule, we are going over time. So I guess into our break.
So I will be that short.
So we need to wrap up. So I think we got good feedback, and we need to play with things and come back, right?
Yeah.
So thanks a lot, everybody, for participation, and we are going for a break until 8:30 in my time zone, which is in 12 minutes. As far as I can say.
Raphael, can you help me see if I can show a screen?
I could, I guess. So let me first try to upload the other slide deck from Srinivas. Okay, so we have that for the next slot.
Srinivas, I think the convention is that you show your video when you want to speak, and you hide it. That way, the presenter knows to call on you, but you're on all the time, so I don't know if they know when.
How do you hide? Okay. That's why I'm thinking I'm always here. That's
yeah, you're always there. It looks like you always have a question. So.
Okay. So I need to.
It's probably there's a blue movie button down on my thing. Press that, and we'll no longer be able to see your guitar.
Oh, so I didn't realize you are seeing all the time. I thought I'm only one.
Yeah, you are on video all the time, actually. So
Oh no, that's not good.
Yeah, you can switch that off.
It's a good thing you're wearing pants. Yeah.
Yeah. Right. So, Lando, I believe that I need to make you a presenter, and then there is a share an external video button or
So
option.
what I have right now is I'm using the video of my face and I'm pointing it at another screen. And so if that works, then maybe, and if people can just full screen that, maybe that's
it
okay.
can. So if you are a presenter, you can. I think you can.
Doesn't look. It looks a little blurry though. I don't know if you can see it. No, I just turned it off.
You can
go back a little.
And sorry to interrupt you guys. Maybe you know, but this platform, Big Blue Button, is supposed to have screen sharing capability. I don't know if it's actually enabled in this instance, but this is what I was told months ago at OSPM.
That would be exactly what I want. That would be much better. But nobody's figured out where the button is for that.
There are three options actually. If you are, I will make you a presenter for temporarily for the time of the break. And yeah, okay. And then there are three options under the plus button on the right, on the left, in the left-hand corner on the presenter area, and one of them is share a video, and I'm not sure what that is, to be honest. I was not. I did not remember this from the.
I think it's a YouTube video. They did it in a different microphone.
Oh, YouTube. So
there
needs to be there needs to be a okay.
No, I haven't made a video, so I can't do that.
Right. So the only option for you then would be to but you can actually, so that you are a presenter now, right?
Okay. So I see tools. I see annotations. I see turn multi-user whiteboard on.
And I believe
share your screen. Wait, there's a share your screen button.
All right. So there you have a
your entire screen share. Let me know if this works, and then what I can do is I can go to.
Yeah, you are sharing your screen.
Now there's Windows going on.
Yeah, that's fine. Let's just see if share1.org. If I go here, can you see my browser, and is it like legible if I go?
Yeah, we can see.
I mean,
okay, this would be ideal because I can.
All right.
I'm going to go to the web page. Okay, perfect. That's great. So I don't have to.
Where's the button, by the way? Because I didn't see it.
Okay, I'll stop sharing because it went away.
Oh yeah.
Actually, let me go back. I'm trying to find out what tab you're on. Big Blue. Okay, so right here, if I share my screen and I go entire screen, application window, or Chrome tab are my choices.
Where's the button? I mean,
yeah, if you see my screen down here.
No.
Okay,
oh, no.
see way down on the right. Yeah, I got to share your screen, my webcam, audio, and mute button. So when you're a presenter, you got a share screen button that you didn't have before.
I see.
And right now I'm going recursive and I'm blowing the thing's mind. So.
All right, so I will take a presenter from you. Sorry about this. And share your screen. Yeah, there is one. Okay.
Great.
Yeah, that's that works.
All right, that's a relief because I'm really bad at making slides while I'm watching another presentation.
Yeah, that's a problem.
So in terms of visibility, you might want to zoom up the page before you start reading off of it. Like the bigger titles were visible, but not the smaller text.
When I was sharing my screen?
Mm-hmm.
Okay. So I'll be able to do that live. So just if you can't see something, because I'm going to be going to a bunch of different pages, just tell me, make it bigger. If you can help me that way, that'd be great.
Yeah, I'd be able to do that. When is your talk? Which slide?
I'm at the end. Everybody will be asleep or have gone home for the weekend by the time I'm up.
Okay, I'll be there.
Thanks. Oh, so how long is this break till? Is there a timer on here?
No, there is no timer, so we are at the bottom of the hour. We start at the
Okay,
bottom,
6 minutes.
bottom of the hour. 6
Okay,
minutes,
great.
yeah.
Thanks very much.
All right, coming back. So in this part of the sessions, we will start with Srinivas's topic regarding thermal management. Let me go to his slides. No. Okay. All right, so this is the slide deck, and now I will give you the presenters, superpowers, and then off you go.
Okay, got it.
You should be a presenter now.
Thanks again for patience. I didn't realize that everybody's seeing me all the time. Maybe I was doing not funny things. So, so the next topic which I have is for, again, clients. Coming back from server to client is the one problem which is getting increasingly problematic, critical thermal trip. And as we know, the clients are running very close to their thermal limits, because of performance reason and the form factor. The critical strip design in the Linux core is it's still very old style. It's like, oh, you have one spike and you basically, your kernel will shut it down. And this problem I have from many, you see, if you look at kernel, like at least Ubuntu or somewhere, Bugsy, like, oh yeah, I got this temperature and I got power down. But that temperature was not really a sustained one. It just, came one spike and it's just, you killed your PC immediately. The other issues which we see also, and a lot of time in all this, many OSs and distro, also there is an option in BIOS sometime is boot to max performance. So when you start your booting your system, it basically performing to the maximum, and it basically putting enabling all the power knobs for max performance. And by the time boot completes in the long boot, yeah, you'd already down once and you reboot once. So that is also observed in some of the very, very tiny form factor devices. And at least in Intel cases, the trips are configured in ACPI, and ideally, most of the time, those laptops are not really designed for Linux. Primarily, it was designed for some other OSs, and they never thought of Linux. Some vendors, of course, many of the top vendors do that, but some of them don't. And those are not optimal for Linux, so it will immediately power down. And also the thermal trip, as I say, it's not really designed for newer style. Like at least in CPUs, you may hit critical trip and you may be staying there for pretty long. It's not really a problem because the CPU will do every kind of things not to move in one degree from it. But it's not like it's not as critical as it used to be. And there are other sensors like skin, or like you have like 15 plus sensors, they just come once violation is not really a problem, because it's like if a skin sensor got once hot and just come down immediately, it's not a problem. The problem is anything which is sustained. So so I have some changes which I am trying to do for test on some of our platforms. So we don't really do power down on critical trip. And it's like I take 3-point runtime average, and it is the very similarly which I did for x86 thermal throttling, where there was a lot of thermal throttling noise before. So what I look for is I have a delayed work queue and take the continuous samples, and if the trend goes upward from critical trip after 3 seconds at least, then I will start, acting and a power down. Otherwise, I'll just, continue to calculate this average. And once it drops to critical trip, then of course I will cancel the work queue. So it's something is happening in I'm doing in our drivers. But the problem is, the thermal drivers are scattered everywhere. Like we have thermal registry from Wi-Fi area, we have registry from ACPI, we have thermal. So it is doing a central place. Ideally, makes sense in the thermal core. So that's my idea is to move some of this processing to thermal core, and and move this as a conditional when you see the register thermal zone. You say that I don't want my critical trip to be handled normally. I just want them to be averaged out. So that's my current design. But I feel that I'm thinking that this is a problem for everyone. I don't think it's a very isolated problem. So my question to here is, don't in like ARM very phone-like devices, do you really handle critical trip in the kernel?
Question. Just to clarify my understanding of what you said. So you said a minute ago that there are scattered like participants that register those critical points, right, in different subsystems. Is that correct?
Yeah.
And you want the behavior to be consistent between them, right?
Yes. Yeah.
This is what you're saying. Okay.
So is it something which is going to, if you want to take advantage of it, or I can live? Do you care if I move to core, or because I feel that phones have similar problems, right? You don't want to really power down your phones just by some isolated incident.
So is this just 3 samples over 3 seconds? That you said that's one sample a second, right?
Yeah, but it's running average, right? It's continuously, last three samples. So to get the trend, I use last 3 samples, basically running average of last 3. Yeah. So.
All right. I guess we are asking for input on whether or not this is a good idea. Do other people have similar problems? Do they think that they can be addressed in a similar way, and so on, right?
Yes. Yeah.
So critical, to answer your question, if the critical 3 points are handled by the mobile, so the answer is yes. There are a lot of critical points.
Yeah, but are they handled by the kernel, or are they handled by an external entities like daemons or things like that, or some runtime?
No, it's by kernel, in kernel.
In the kernel. And do you have the same problems, like they can trigger a system shutdown prematurely in some cases?
I never seen that, but I don't have all the experience of the stock vendor.
Oh, I
Lina
see. So
would be more.
So I guess the question would be if we are less strict about handling them, like Srinivas said. So we are not going to trigger system shutdown immediately on crossing the trip point, but rather we'll wait for a while, and then if the trend is upwards, then we will trigger the shutdown, and if it is not upwards, and we will still be waiting for it to leave the red zone, let's just say, and then continue, possibly to avoid premature. So the goal is to avoid premature premature shutdowns due to critical trip points, right?
Yes.
Which happen, and so if we did that delayed handling, like Srinivas is proposing, would that be a problem for the larger community?
So in my opinion, it should be left to the platform to decide. So a lot of ARM platforms also have firmware support. So even if your critical trip point, if the spike is, if the slope is big enough and you're going past your critical trip point, I mean, the firmware might take care of that. But in general, I think that if you've reached the critical trip point on a mobile device on your phone, something's gone wrong. So it's probably a good idea to shut down.
Okay.
I don't think 3 seconds is going to fix anything on a mobile platform. So I think there should be the option for platform vendors to.
Yeah, and I think this can be a post zone attribute. Right?
Yeah, I currently that's what I did. This is conditional, but yeah, I was just thinking, anytime the thermal zone register already has so many parameters. That's why it's like it's becoming a base dictionary there. So yeah, okay, I see the point. Yeah, I will make sure that it should be conditional. Yeah.
And what difference do you do between a hot trip point and critical trip point in this case?
We don't have a hot in the at least category in the ACPI. Really, nobody used it. We basically in hot trip point we achieve we take to user space and daemon and we put it to the sleep. Not it basically suspend to whatever suspend mechanism. We don't really reboot, but we put to suspend. But not kernel doesn't handle that. At least none of our devices have hot trip points.
So is critical from the critical trip point is it considered as a very dangerous trip point?
That was the case a long time back because in the CPUs you hit that trip, you better trap it down. But as I say, now firmware is handling so many things. It knows that I reached that critical trip, and it will do everything to keep it under that. It's not really going to. It's most of the device self-protecting. It's not like it's not giving kernel to do all these things anymore.
Okay.
So yeah.
So in this case, it makes sense that allowing some room for the critical result.
Yeah.
Okay.
Okay. Yeah. I see that. I'll propose this as a condition.
Yes. If it's conditional, I think it's fine.
Okay. Yeah, that was my short presentation, this one. So since I took extra time last time, maybe I can compensate here now. Rafael, you can take over.
Yeah. Okay, thank you. I guess so. I hope I got the notes right. Please have a look and see if I'm not sure about whether this was hot or hard, by the way, but you were talking about the categories of trip points,
hard,
right?
Yeah.
Hard.
Yeah,
okay,
hard.
That was my understanding. But anyway, so okay, thank you. So we have two choices. Basically, we can switch over to the next topic right now, or we can wait until this. It's due time by the schedule, but I think that we are at how much time? 10 minutes ahead of time, so we can switch over to it right now, and maybe there will be some more room for the second next topic. To this end, so who's going to be the presenter in the next one? Tara, I guess. Yep.
Yeah. Yes.
All right. So I will take the presenter for now, and then I will have a look if there is. Do you have slides for this topic?
Yes, I did upload them to the.
Oh, they have been uploaded. Okay.
Yeah,
So thermal warming. Okay. Nice. So let's switch over to that, and I will make you a presenter, and off you go.
Okay. Are we starting now?
Yep. Yes. Let's just start the thermal warming topic right now.
Okay. Hi, hello everyone. My name is Tara. I work with Leonardo, and I'm here to discuss some requirements where the kernel thermal framework needs to handle lower temperatures as well. So before I go through what we are proposing here, I would like to take a few minutes to discuss the problem that is faced. So like everyone knows, a circuit usually consists of multiple gates or elements, however you want to call it. And there is an intrinsic delay involved in signal propagation from the input of a gate to the output. And the accumulated delay of these elements become the delay of the circuit path. And this accumulated delay ideally cannot exceed the time period between one time period between the synchronizing clock pulses. And if this delay exceeds, what you will essentially see is the circuit not functioning properly or a circuit malfunctioning and all that. So to avoid this, typically SOCs are characterized for timing closure in a particular temperature range. So they say that within this operating temperature range, the SOCs can operate, or different parts of the SOCs can operate at various voltage and frequency combinations. Now, what happens is if the SOC operates at a lower temperature than what has just been characterized for, some of these voltage and frequency combination will lead to the timing closure requirements not being met. And this would, in fact, eventually lead to a non-functional system. And how to avoid this, what needs to be done is to increase the operating voltage itself. So there can be handled in multiple ways. You can say that, okay, I will always operate at a higher voltage, which is probably not the most power efficient solution. Or we can always also say that if the temperature starts dropping below a certain point, we prevent certain lower voltages or turn on some resources so that turn on some voltage resources. So if you really look at it, it is opposite of what needs to be done. What is needed here is the opposite of what needs to be done to cool down a system if the temperature rises or goes beyond a certain point that has been defined. So this is again, so the solution comes from that fact that it is opposite of what the thermal framework does today. So the kernel thermal management framework today does have the provision to monitor and handle the out of bounds temperature. The caveat here is that it only handles rising temperature. It only handles them if the temperature goes beyond a certain point. So the proposed solution is what we are proposing here is to extend the framework to monitor and handle falling temperatures as well. And out of this problem and the proposed solution, we have two new requirements that can be added to the thermal framework. So one is that the thermal framework should monitor and handle descending temperature, and two is that thermal framework should support warming devices. By warming devices, what I mean is the mitigating action that needs to be taken if the system falls below a certain temperature limit. And okay, so what I did here was to divide the kernel thermal management framework into multiple pieces and to see which all pieces needs extending to support these requirements. So the first piece is the trip points itself. So what trip points are nothing but a point in the temperature domain upon crossing which the framework is supposed to initiate a mitigating action. So all the trip points that are supported today, like active, passive, the critical that we talked about, hot, all of them handle only rising temperature. That means if the temperature goes beyond that point, that is what those trip points indicate. So the proposal is to introduce a new trip type called cold, thermal trip cold, and also introduce an associated device tree property with it called cold. So I had
a question here. Do you anticipate more than just level, more than just one level, right? So do you think that there will be only one cold trip point, or there may be two, like cold and very cold, for example, like something like that?
I'm not sure. So I have seen only one so far.
Okay.
That could be very cold as well. You mean something like critical on the other side?
Critically on the other side, yeah, exactly. So if you cross that, then your SoC pretty much doesn't work anymore, right? Because
So, sorry, at least based on my experience, I think probably you will have a cold a trip point beyond which you want to warm it, and after that, if it goes below, you probably is going to just shut down. I don't think you'll have multiple more than that based on how SOCs are typically characterized. So they characterize for the lower temperature bounds. They're not going to have multiple regions typically to characterize because it gets more expensive if you do that in terms of manufacturing.
Okay. Yeah. Okay.
So, I have a question here. We do have some, some RC sensors, some which is shows negative values, means like more temperature. It's like, higher negative value, in the sense. So we convert that into the, basically we negate that negative, and like we register based on, we know that it's like, whenever we present the temperature to the core, we already take care of that negative factor. Can you not do similar here, instead of creating new framework for it? Because you just know that, higher negative temperature is basically is a problem for you. Instead of creating a special trip, you just in your driver.
I'm not sure I'm following. So can you maybe rephrase a bit? Like, what is the negative temperature? The temperature is in Kelvin, right? So it's always positive. Or
yeah, like your sensor is giving in negative. Like it's like -40 is big. Temperature is lower than -50 type thing. So scale is negative. So when we convert, we just change the sign and present it to the score, so that it is, like.
You mean that instead of having the cold, you could create a set of trip points with negative temperatures, and then go and then convert them to positive, like multiply by -1. Before going to the core. Okay. Well, I don't know.
Yeah,
but if you have then you have to go a negative cooling device then to warm it up. I get it. I think it gets
warming is done by your cooling device. It can take whatever it does, right?
Right. You would think this would be general.
Yeah.
I mean, we should be able to trip in both directions, right?
Yeah.
Right.
Yeah.
It doesn't matter if it's negative, positive, or absolute Kelvin. We should be able to trip in both directions.
Yeah.
So so when I did this first, what I had done was not this thermal trip cold. The very first patch set that I had sent out for RFC for this was to introduce a direction for monitoring the trip type, which would say that at a trip point, which would say that for a trip point, you could either monitor it upwards or downwards. So like I don't know who spoke now, who said that you could monitor it on both sides at trip point. So it was something like that.
Len Brown.
All right. So for a fan, when the temperature increases, we always talk about it increasing. We hit the trip point, we read the temperature, we say, oh, we're above that trip point, and we turn on the fan. Well, guess what? We also hit the trip point going down, we read the temperature, we say, oh, we're below the trip point, and we turn the fan off. So a warming device is basically the same as turning a fan off. And guess what? You would turn off the warming device after you get warm and you cross the trip point in the positive direction, right?
Yes, but that entire monitoring, whatever you just now said, doesn't exist in the framework the way it is. So
okay. So what I'm saying is this warming device is the same as a fan.
Okay. Yes, it is. Yes.
It's the same as a fan, because a fan doesn't actually have to be a fan. It could be a lot of things. It could be a throttling mechanism, right? It could be anything. And it works in both directions. There's on in one direction and off in the other direction. The only difference here is that the warming device is on in one direction and off in the other direction.
Right.
Yeah, that makes sense. Yes.
The action is up to the device. What it does, I mean, you could have it, I don't know, have streamers come out the side, come out the fan or something, or it can be anything. Basically what you're saying is you have a special fan, and what this fan does is it warms the system when you cross the trip point in this direction, and it stops warming it when it crosses the other direction.
Yes, that is right. But the only question is, how do we indicate this in the framework itself? when to stop that particular monitoring that we are talking about, and when to trigger the action, the fan turning on or the...
Today there's a number of tricks that are done with cooling devices. Some are, for example, you may have one fan with multiple speeds, but it can appear as multiple trip points. So you cross one trip point, it's low, you cross another one and it goes to medium, and you cross a third one, it goes to high, and it does the reverse. I mean, the thermal subsystem doesn't know that the fan is doing this. The fan knows that it's doing this, right?
No, but you have to. Oh, yeah, okay, yeah, okay. That's right. So when you, so there is a, I believe that there is a number of devices which you activate, sort of, quote unquote, when crossing a trip point, or.
Well, you tell it that you crossed, and it reads the temperature, and it decides what to do based on that notification, right?
Right.
So yes, but that is where the governors come in, right? The device itself doesn't take that decision, right? The framework takes that decision for the device, right?
Yeah, but you can send, instead of introducing another trip type, you can, in your somewhere you can set that, like direction may be more better instead of creating another trip type, right? Like you can say that anytime you trip, you multiply it by -1, or
And then notes here to note this down.
But is it possible to have cold trip point with positive values, like 5 degrees, for example?
Oh yeah, it is. It doesn't matter. So the scale is whatever scale of temperature you use. But the point is that you have a constant. You have a scale of temperature going from min to max, and then there is a number of trip points on that scale, right? And then you can cross them going upwards, or you can cross them going downwards, right? And today we only trigger actions when we go into the upwards direction.
Yeah,
but conceivably we can trigger actions when we go in the downwards direction as well, right?
Yeah. Another way to think about this is, like, I guess having your operating temperature range, say, be from -20 to, I don't know, 80 Celsius. And by default, on a normal room temperature, you would be operating within quotes in a cooling mode, where the cooling mode would be to allow the CPU to go to lower frequencies, right? So your cooling device would be, okay, I'll allow the CPU to go to the lower frequencies and voltage because that's okay to operate, say, between 0 Celsius and 60. And then when you go below 0 degrees centigrade, then you can say, okay, I'm going to stop cooling because I don't need to cool anymore, because I'm now in the range of, say, 0 to -20 Celsius. So I don't need to allow the lower frequencies or voltage levels to allow for cooling. I guess that's another way to look at it. You don't have to do any negative multiplication or anything.
Right. So you can turn all things on and off, right? So when it's like a fan. So this is what Len said. Exactly. So when you cross the trip point in one direction, you turn it off, and when you cross in the other direction, you turn it on.
Yeah, so that is what it is. So there are, if I come to warming devices, there are some resources like that, which, like, but at least what we have seen is there are some resources that just needs to be turned on, just because we are falling below a certain temperature.
Right.
You just have to turn the resources on and nothing else. That's all. That is your mitigating action.
Yeah. Right. I think the point is just that if you shift the scale and let it go below 0, then you don't need to do any special thing. You just can flip your
that's what
device.
Srinivas was suggesting, right? And if you reverse the scale, then you basically get the
Not really
same...
reversing the scale, but you just like making the window larger for the scale. You can still have negative numbers, it's fine.
Right, but then you don't. So the question now is, if the how much of what changes need to be made and where, right? This, and what would be a better change or less intrusive change. So there is a number of ways in which you can address this particular problem, and that one of them it would be, so yeah, there are at least 3 I can think about right now. So one is to introduce a new trip point type. and then and all of the make all of the changes following that. The other could be to add a direction notion to the existing framework, and then trigger actions both ways, right? Which you still need to do to some extent for fans, for example, because if you have turned the fan on when crossing a certain trip point, and then when you go back with the temperature, it falls down, then you need to turn the fan off. And the warming device in this case is exactly the same thing, except that the on action, the actions are different, right? On crossing upwards and downwards, but the actions are represented by some callback, I guess. So this doesn't matter to the device. Needs to handle this, and then the other would be to do what Stream was suggesting, that you could introduce a negative section to the temperature scale, and then when you go below 0, then you will just multiply everything by -1 and present that to the core in the same way as previously. I don't know honestly at this point which of them is the best way to do it.
Wouldn't the negative kind of conflict with the real positive temperatures too? I'm not too familiar with that. That's the main worry for me.
Yeah, but you only look when you go 0. Yeah.
That needs to be investigated, honestly.
Yeah, because that would really depend, right? Because usually, I don't know, at least what I have seen is that the positive temperature ranges we define as really high, like 65 or 70, or even above that, 95 and stuff like that. I don't think we're talking about the chips going really to -95 or -65.
Yeah. And I prefer not doing the negative multiplication and taking it, just too confusing. But yeah. We just should allow negative temperatures in thermal framework and call it a day if it's not already true.
So this is the latest RFC that I had posted as far as thermal trip cold. So I had presented this at ELC. We had done that, and so after that I did a little bit of work on it. So that is the RFC out there. But then I think a year ago or something, I had posted a patch series with this, instead of introducing a new trip type, that had introduced a direction, like what Len suggested, which said whether it
right, or at least. Yeah, or at least try to do that, and if you get something simpler, then maybe this is the way to go, right?
Okay, so I can probably dig that out and post it out again and see, we can compare it.
So I haven't really been involved in the thermal stuff for about a decade, but it used to be that internally everything was done in Kelvin, so this plus minus stuff didn't come up. In ACPI, things are internally in Kelvin, and we represent it in Celsius.
They are. Yes, it is what I remember.
Yeah, then problem is solved.
Yeah, so
and that's sort of absolute is a great word. It's an absolute scale. You never go below absolute 0. A trip point is a trip point. The direction is up to you.
Right.
Yeah. Only thing we need to, when we enhance thermal, we need to make sure that we don't present too many things in the thermal CFS to user space. That's already crowded. Too many entries. For user space to poll, to really come up all the time, it has like 20-30 entries already. So I have to go another trip type and find out what it does. It's a lot of tax. Minimizing the user space exposure would be very preferable.
Okay.
Yes, I think the most simple way is that. Can you hear me?
Yes, I can.
Yes, you can.
Yeah, I got some noise. Yeah. Okay, so I think the most simple way is that we just treat it as normal trip point. For example, if we have a trip point at for example at 0 degrees Celsius, so we have a CPU device, and its minimal its initial state its cooling state 0 is 2 gigahertz, and it can be we can set it to like 800 million hertz as the max cooling state, right? So so we can just bend this cooling device to the 3.0 Celsius directly, and then, for example, if we are in a normal temperature like 20 Celsius, then the system is just running at a kind of overheating state, right? Because the CPU will be throttling to 800 megahertz, right? And only if the temperature is lower than 0 Celsius, we will set the CPU to state 0, which is 2 gigahertz. So this is actually warming, right?
I'm sorry,
Mm,
I think he's repeating the.
Following.
I think he's trying to say the similar thing I said before. If it goes below 0, let the CPU warm up by disallowing lower frequencies. I think that's what he's trying to say.
Yeah.
So I think I got a 5-minute warning, so I'll just walk through the next few points and then we can take the discussion outside.
Actually, I'm not sure if we seem to have time because the next topic starts at formally at 20 past, so it's like we have 15 minutes still before the official start of it, and if we if we finish earlier, then fine, but we can use up all the time, I guess.
Okay.
For the discussion. So I in my like takeaway for now is that the one possible other way to go would be to try the direction thing, right?
Sure. Yeah, sure. Definitely. That's something
yeah, and you basically with that you don't need to have the new thermal trip point type because that can be a
yeah, you don't have to have a trip point type, but that will also involve a DT property, which will say that what is the direction basically, whether it is falling or rising or however we want to define it.
Yeah, no, but what do you have? How do you deal with fans? Like a fan has two directions, right? Kind of cooling fan, right? So if you cross the trip point in one way, it will trigger an action, and if you cross the trip point the other way, it will also trigger an action on a fan.
Right. You read the temperature and you decide what to do at that temperature. And so if you crossed into positive territory, you speed up. If you crossed into negative, you slow down.
Right. It doesn't have to be positive and negative if you are above and below, right? The
exactly. Right.
This doesn't.
And
And the action and in principle the actions are not defined as speed up and speed down.
They could be anything. It could be anything.
Could be anything.
It could play a sound or make a smell come out of your computer.
So for this particular device, you can it's like a fan has two actions. One is triggered when you cross the trip point going down, and one is triggered when you cross the trip point going up.
Right.
And what the actions are depends on the device.
Right. Yeah, so the actions are not dictated by the framework itself. It's part of the device. Just that what action is, when to take the action and what action is dictated.
When you go up, you trigger A, and when you go down, you trigger B.
Yeah,
And the device definition is what defines the A and B.
Yeah,
right?
Yeah, exactly. Yeah. Okay, so moving on from the trip point type, the other piece to this is adding support for monitoring and mitigating a falling temperature in the framework. I think it should be part of the governor, but I don't have a solution to this. The question is, do we extend the existing governors, like we can extend the stepwise governor or maybe even IPA to handle falling temperatures as well, or maybe we need to think about new governor which will handle a range of temperatures for the zone, which says that, okay, I will make sure that my zone doesn't go out of bounds of the specified range. So when it's out of bounds, it's both monitoring falling as well as rising temperature. So I don't have a solution. It's just
I think you need that. With the direction, you need that because your hysteresis is a band.
Yeah.
Right. And then you put the direction, and pass it to the governors, and then if it's out of the band, they will do currently it takes direction one side and take both directions, right? Yeah, so that's, I think, still reasonable to extend this governors and shouldn't be complex, I feel. I mean, I don't have IPA. IPA may be complex. I don't know much. So
yeah, and I think I don't know much about IPA, but if there's any kind of hysteresis, that's definitely not acceptable though for this one, because once you go below 0, you want to immediately start warming up.
Yeah,
but you have like those temperature fluctuation, right? It's not like just stuck there.
Sorry, I'm not sure I get your point here.
I'm saying that, you're saying 0, if you don't have hysteresis, then you will have, your decisions will oscillate all the time, right?
Okay, hysteresis isn't coming out of the, one way is fine. Basically, I'm saying you need to treat it similar to the critical at the other end. So because other intermediate ranges, it's okay to do some averaging or whatnot in terms of temperature. But for this, I don't think you can do that. That's all I'm saying.
So hysteresis is always only to come out, right? It is never to go into a state, right?
Yeah.
Hysteresis is always when you come out, like as in basically stop your mitigating action is when hysteresis comes into picture, right? It's not to get into the mitigating action, right?
That's correct, yeah.
So yeah, so like you said, extending step. I'm sorry, go ahead, Daniel.
In the case of passive cooling devices like CPUFREC we have, the CPUFREC is using the PMQS to set the frequency for the min and max constraints. What happens if we try to change? We will be changing the semantic of QS in case we want to warm up. It will be different from mitigating.
Why do you need to do that? You just take your minimum up, right?
Yes, but that will be different. Right now, we cap the OPP. We prevent to go on an higher OPP. We will do the opposite. In this case, we will need to cap to put a minimum OPP. So that means that has an impact on the cooling device. We will need to do a change inside to make sure that it's able to warm up.
Yes, so that is the third part here. That comes under warming devices. I've listed that down.
Right. You mean the definition of the driver, the cooling CPU cooling driver, right?
Right.
Daniel, you mean the CPU cooling driver? Yes, that's correct. So it needs to be extended for that, right?
Yes. So then so I did talk about the governor and how maybe we can think about extending stepwise as a starting point and then see how to go about it. And then the third piece, is the warming devices itself, which is kind of.
I think Eric is trying to talk. Let's let him finish. Otherwise, his background noise is too high. Go on, Eric.
Yeah. Thank you. Do you hear me now?
Yes.
Yeah, perfect. So I have one comment to the using of heating device when temperature is low. Because lots of these devices, like phones and laptops, are operated from lithium-ion batteries, which are not very happy when temperature is going down. So draining power from these cells is a very bad thing in low temperatures. And I understand that when we are going down to SOC limits, we need to heat it up. But if SOC limits are, for example, minus 20 degrees Celsius, and there is minus 10 degrees Celsius around, we just shouldn't start to waste energy to heat it up to 0 Celsius or something like that, because we will not reach those limits, and we just will drain battery much faster.
I agree. So that is what you will define with the trip point, as in your temperature at which you should really start doing the initiating the action. So it could be 0. It could, like if the SOC itself is characterized to lower than 0, it can, you say it can operate at minus 10. So it could be minus 10 or minus 20 or whatever that is.
Yeah.
Also, there may not be a battery, right?
Yeah. If it's in device without battery, it's okay, probably. Yeah. Thank you.
Consider a device that's sitting on the top of a phone pole in the middle of the winter near the North Pole, right? And it has
Eric,
power.
can you mute yourself when you're not talking?
Yeah.
There's a lot of background noise.
Cool. Thanks.
And I believe that a Tesla warms up its battery to make it more efficient. So at some point there's a crossover where taking energy out of the battery to warm the battery is actually a win. Just saying.
Not sure about that. It's like contradicting the second law of thermodynamics or something like that. Anyway.
Not actually. These batteries are able to give you around 1/2 of the capacity when they are around minus 10. So if you will waste something like 2% of their capacity to heat them up, you will get almost twice the energy.
Yeah.
That's
Anybody with
how
an
it works.
electric car in the winter experiences this.
Yeah. Okay.
Yeah.
Fair enough.
I have that car.
Yeah. Fair
Okay,
enough.
so I am moving on to my third piece because I still again got a 5-minute notice.
Well, it's like 3 minutes left now.
Yeah. So, okay, the third part is the actual warming devices itself. So like I said before, some of it is just turning on a resource. They are simple, nothing to do. You just make those essentially the cooling devices in today's framework, and it should just work. But then we have also had resources like there are power domains whose performance levels have to be increased, or like Daniel brought up, there are disabling of the minimum operating points of certain devices like CPUs and GPUs. That is the other kind of warming action that can be triggered.
Right, so you have a number of drivers that only work in one direction now.
Exactly.
So basically, the trick would be to change them so that they can work in 2 directions instead of working in 1 direction.
Yes, so that is true for the stuff that is already existing, like your CPU FREC, for example, or even dev FREC. But then there is also this question of power domain based, so turning or basically taking a power domain to a higher level. So that would require a new kind of driver that needs to be introduced.
Doesn't power domain use OPPs too?
Yeah, that should be handled by the OPP framework, as far as I can say.
Right. I mean, I don't know if OPP framework. I mean, there's one thing I've always thought of, but it's not true. In OPP framework, you have enable, disable. If they're ref counted, they could have been used for something like this, where you can disable, and until the disable ref count goes to 0, you don't let it be enabled. So there's like enable and disable. So you could just go disable all the bottom OPPs that you think shouldn't be used, and then everything should automatically settle at the higher OPP, or we can hook it up to PMQoS.
Right. So
I'm not sure I understand what you just said.
So OPP framework, you can disable, enable individual OPPs.
Yes.
So that's one way of disabling lower OPP points, so to cause it to warm up. But the only problem is if some other driver comes and says enable, it just gets enabled. It's not ref counted. So if that is added in there, then you could use it as a way of enforcing it.
Right. All right, we have used up all of the extended time time window for this topic.
Yeah,
so
but
let's
I think
move
that
on
was
to
all
the
I
other
had
one.
anyways. So yes.
Okay, so you got quite a lot of feedback from different sides, and then now it's time to try different things and come back.
Yes, I think, yeah, I will probably post something onto the mailing list and we can continue the discussion there.
Right, thank you.
Yeah, thanks for listening.
Okay, so now is the time for the next topic, which I'm involved in somewhat. So I will take a presenter. And now, so Francisco, my idea is that I will give a very short introduction to this, and then I will switch over to your slides and give the presenter to you. Sounds good?
Yeah, go for it. Can you guys hear me right?
Yes, we can. All
Great.
right, so I will just use my very short, very small. All right, so the title of this topic is performance improvements in power sharing scenarios. But so why this has come up in a couple of times already. And even was discussed in the LPC in the power management micro conference a couple of years ago without thermal. So basically, this is about situations in which there are multiple components sharing a power budget, like the processor and some other devices, but not only that. So let me start with the observation that there are adaptive CPU performance scaling governors like schedule till or on demand or interp state in the active mode, which basically try to prevent energy from being wasted. So there is a strong assumption there that the degrading performance should be avoided because people don't like losing performance. Unfortunately, maybe some of them will be willing to trade some performance for some energy, but the general trend seems to be that there are not too many of them. So the governors in question try to adjust the operating frequency of the CPUs to what is needed, and the measure of what is needed is the utilization frequency invariant utilization of CPUs. And that is kind of works in many scenarios, but there are cases in which it doesn't work. Now let me go to this. For example, what if the utilization is 100%? Right, so the governor then assumes that the user needs the maximum performance, but this is not necessarily the case. For example, if the workload is memory bound, then increasing the frequency of the CPU beyond a certain point is not going to make any difference because the workload is CPU is memory bound already, and it is not going to be running any faster anyway. This is not harmful. I mean, you can increase the CPU frequency.
It can be very harmful. You can double your power doing this.
Yeah, this is in terms of performance. Okay,
right.
It is not harmful in terms of performance. It can be very harmful in terms of energy. That's true. Okay, the other type is when you have components sharing the power budget with the processor, in which case, if you attempt to increase the CPU frequency too much, it will actually hurt performance. So the performance will decrease, and that's something that people don't like a lot. So, and at this point, I would like to give the floor to Francisco so he can discuss one
Can you enable downloading this slides when you're presenting?
Yeah, I will. Just a second. Okay, sorry about that.
And is there something you need to do in order to upload my slides to the program as well?
I've already uploaded them.
Oh, okay, cool. Just because I don't think there is going to be enough time to go through all of them, so that way people can look.
Okay, good. So this is, I will now switch over to your deck. And give the presentation. Okay. All right. And Francisco.
Good. So my name is Francisco, and I work for Intel. And I've been working on this project for quite a while now. And it's kind of a common misconception that its purpose is to improve the situation with power sharing scenarios, like to the point that it's this misconception is even reflected in the title of this slot. But the actual purpose of my work is to reduce the energy usage of the CPU in some cases where it doesn't affect performance. Specifically, whenever the CPU has a bottleneck on a different I/O device, there is quite some opportunities in order to share power, to reduce power usage. And of course, as a side effect, this has some potential to improve the overall parallelism of the system and the throughput whenever throughput is constrained by the amount of power that can be supplied and dissipated from the system. But also, it has some potential to improve battery life or reduce the cost of running the system. So in order to illustrate, even though Rafael already pointed out some of the connection between the two topics, so these few slides are intended to show the connection between the two things graphically. So in this graph, you can see how the power efficiency curves of two different actors sharing a power budget vary with power allocation. And so in this case, you can see that processor A, the blue line, is slightly more efficient, and the orange line is slightly less efficient. And the overall energy efficiency of the system is the green line, which is sort of the linear combination of the two lines, right? Where the weight of this linear combination is the fraction of power allocated to each one of the processors. So for this graph, the basic assumption is that the workloads running on both processors are independent. Which means that the performance of processor A and processor B are basically independent variables, except for the fact that they are sharing a common budget. And in this case, as we can see, so the next slide is showing to you it's showing to you the power curves of the same processors, right? So these energy efficiency curves are just calculated from these power curves. And as you can see, the peak of the overall system performance is located at exactly the same point as the peak energy efficiency. And actually, the overall efficiency curve is directly proportional to the overall performance curve, which I guess shouldn't surprise anybody, because given that energy efficiency is no more than the ratio between performance and power, assuming that the denominator is fixed, assuming that you're running at fixed power because that's your maximum power budget, performance will be directly proportional to your efficiency.
So power is easy, but are you measuring the same performance on both processors?
Not necessarily. So as you can see, at the maximum efficiency point, neither of the two processors is running at maximum performance, and neither of them is running at maximum efficiency either. Instead, the optimal balance is characterized by maximum overall throughput.
Okay, my point is this. Say you have two fishermen. One is fishing, one is cutting bait, right? And they might be, I don't know, you give them both some resource, and one of them cuts a lot of bait, and the other guy has to fish. And what you really need is the fish and the cut bait to match evenly. right? So it doesn't.
Right,
One
exactly.
can be
No, in this case. Wait a minute. In this case, the assumption is that the tasks running on both processors are independent. So the optimal allocation is not a function of the ratio between the two tasks, because it doesn't matter. In order to maximize the performance of the system
totally
as a whole.
independent. Okay.
Right. We are going to get to that situation you're talking about just in the next slide, because actually this case where the tasks are independent isn't something that my work is even attempting to address. So and this is why I was saying that the primary objective of my work is not to deal with every power sharing problem out there. Since like the goal is somewhat overlapping with that, but there are cases like this two independent workloads where it won't help, because my optimization is something local to the governor of each one of these specific processors. So assuming that each one of them is unconstrained by any external agents and is able to utilize the maximum performance of that core, it's going to attempt to draw as much power. And you need some external agent like a IPA, for instance, in order to orchestrate among them. But this is an explicit non-goal. However, now we go to a different case where the performance of both processors is interconnected. For instance, the case I've been dealing with primarily is where processor A is the CPU and processor B is the GPU. And in order for the GPU to do anything, it needs to receive work from the CPU, and vice versa. The CPU cannot simply make unlimited progress without having to wait for the GPU at some point, because at some point the GPU is going to have so much of a backlog that it's useless for the processor to continue submitting rendering to it. So at some point, either needs to wait for each other. And as you were saying, there is a sort of an optimal ratio between the performance of both co-processors, which is what I denote by K in this slide. And also, as you can see on the performance versus power allocation graph, the curves for the two processors and the total performance curve is heavily correlated. Like in this case, it's exactly directly proportional. And also on the left side of this red line, you can see it looks suspiciously similar to the power curve of this processor A, because processor A is the bottleneck on this region. And at some point, as soon as processor A has received enough power in order for it not to be the bottleneck shifts to processor B. And from that point on, as you can see, the power curve of the whole system looks very similar to processor B, which means we have reached a bottom on the other processor. As the maximum performance of the whole system is achieved at the intersection of those two regions. And the other interesting thing about this slide, which you can see, is from this optimal point on, performance, which is something Rafael already mentioned. Performance is strictly decreasing with increasing power, assuming you're looking at it from the perspective of processor A. So, assuming that you were able to control the frequency states of processor A in the most efficient way possible, you will be able to reach this red line as close as you want. Now we're going to talk about how we can improve the efficiency of the processor a bit. And this does rely on some knowledge about the power curve, but it doesn't require a full energy model. It really only needs a single point out of the power curve, which might seem like a limitation. It actually makes the algorithm quite robust. And I think because of this, it also has the potential to be ported to pretty much any processor out there. because the only feature we're gonna about the power curve is that from this this one point we know about, we call the most efficient frequency point, the processor curve is convex, and this has one straightforward consequence, which is almost equivalent to the, it's equivalent to the mathematical definition of convexity. Any linear combination of points, like for instance, the average power consumed by the workload is no more than the linear combination of the power consumption at each specific state that the processor is running at. So this linear combination is guaranteed to be greater or equal than the power at the same point of the curve, which averages the same performance, which is what we can see on this graph. So here we are comparing the simplest possible linear combination of points, which is just a linear combination of the maximum frequency of the processor and the minimum frequency. Well, this as you can guess, it's an idealized power curve, but given that we are using no specific features about this beyond the convexity of the curve, is actually fairly accurate depiction of the behavior of the processor. And as you can see, it assuming that the red line denotes the average performance we are getting out of the processor. If we are achieving this performance by averaging between the maximum frequency and the minimum, we are going to lie over the straight line that joins those 2 points, right? And this is what some people call race to halt power management, right? Just set the maximum turbo frequency as long as there is any work for the processor to do, and as soon as you're done, idle. And as we can see from this curve, this is actually a pessimal strategy energy-wise. So yeah, this graph is a bit intended to deal a blow to this race to halt rule of thumb that has become so popular in the last year. So
just one point, I agree with your
yes.
point that race to halt is abysmal in the situation, but it's not at least obvious to me from the graph how you come to the conclusion. Because
there is actually no way, assume that the average frequency is the one shown on by the red dashed line. There is actually no way to, in order to obtain this performance out of the processor, there is no way to waste any more power than by averaging between those topmost and lowermost states. Okay. So it's actually a pessimal strategy.
Okay. So the thing about this graph is it starts at the origin, right? And the reality is that nothing works that way, right?
Right, that's true. Yeah.
Yeah.
It's idealized, and in reality, the power draw of the processor at zero performance will be slightly above 0 watts. There will be some static power consumption indeed. So in reality, it will be even worse than that. This idealized processor, which has no power consumption at idle, is actually the best you can get for race to halt. And in reality, I expect it to be even worse. So anyway, the conclusion out of this is that if we want to get optimal power usage out of the CPU, we somehow need to find this fixed frequency, which is able to give us the exact same performance as a variable frequency, which may not exist. It may exist or not. In the cases I'm dealing with, the assumption is that the processor has a bottleneck on a different device, right? So the assumption is that at least locally, the performance of the processor is independent to its frequency, right? And okay, so given that the main problem here is how do I find out what this fixed optimal frequency is, since it basically involves knowing 2 things. It involves knowing how much load the application is going to have in the future and how quickly the application needs this work done, which involves...
a really simple question. What do you mean by energy optimal?
it means that in order to do the amount, to achieve the performance we are getting on the average out of the processor, we are consuming the least amount of energy possible.
All right, so you have multiple multiple energy levels at which you can achieve the given performance.
No,
right?
so assuming we want to achieve the optimal power draw for a single frequency, there is only one frequency that can allow you to achieve that, which is, since any combination of frequencies which give to the same.
So going back to my question, what do you mean by optimal energy? Yeah, again,
Optimal energy.
Yes, because this is very unclear.
I mean that for the amount of performance, for the amount of work you're getting out of the processor, you are spending the least possible amount of energy in order to get that done. And as you can see,
if you can, so for the convex curve, as you said, this is achieved by running at the minimum frequency.
At the minimum frequency, which gives you the performance you want.
Well, so the performance is, you have a notion of a specific level of performance that you want to achieve, right?
Yes. In this case, it's the red line, and I'm seeking the frequency control that allows me to achieve this average frequency, this performance with a minimum amount of energy. That's what I mean by optimal.
All right. So now the question is, how do you find this this point where the red line?
Right. Exactly. That's what I was getting to. So given that, go ahead.
So the previous one, I think, a lot of time when we talk even this committee, you're talking about energy efficiency. You should talk energy efficiency in terms of SoC, not a processor. That's where the whole confusion starts. You're optimizing energy for SoC, not because on a processor, it is
actually the two are correlated. Let's go back a few slides. In this case, you are right. You're right. The thing we want to optimize is the overall energy efficiency of the whole system. However, in this case, because both the performance of both actors running on the processor is actually heavily correlated, the overall efficiency of the system is correlated with the performance of the whole system.
We seem to be in disagreement over what goals we want to achieve, because the problem is that this is why I was asking about what you mean by and so on. So really the goal that we want to achieve is we want to achieve a certain level of performance, which is acceptable to the user, right?
Well, I want to achieve ideally I want to obtain optimal energy efficiency out of the processor.
No.
However, because of what I've shown on this graph.
We have 2 minutes left. Okay, let me rephrase. Let me state this again. The user wants a specific level of performance. For example,
minimum performance.
Not necessarily minimum. There is a level of performance that they are going to accept, like the frame rate.
Right.
Something
Exactly.
like that.
You want a minimum frame rate of 30 frames
and
per
that's
second.
a given. It's not like you can determine this without asking a user. That's a given from the user.
Well, not always. Like sometimes the user doesn't even know what performance the system can achieve, right?
But they have a measure of something that they want to get, right?
Of course, the final horizon is to get the maximum performance we can get out of the system at the minimum energy cost. And I guess we can achieve that.
That's what we get at a minimum P state. That's what I'm saying. The minimum P state is the most energy efficient one. Yes.
Right, but that's not my point. My purpose is not to achieve the minimum absolute energy efficiency of the processor, but my point. So listen up. Let me answer to Rafael. My purpose is not to get the maximum absolute efficiency out of the processor, but get the maximum efficiency for the maximum performance achievable. I have this.
Okay, that's fair.
I have this constraint very clearly. The one you mentioned, that of not hurting performance. I still want to keep the system running at maximum throughput, but
all right,
as you can see,
okay.
it's actually decreasing.
Unfortunately, we have used up our time now. We can go into the break somehow, but so somewhat.
Yeah, there are so many slides.
Yeah, let's go into the break. Let's keep going. Let's keep going because I think that we've cut off Francisco.
All right, so let's keep going.
All right. So now let's try to think about how we can attempt to estimate this this F bar, this optimal frequency, which allows the processor to achieve the best performance with the minimum energy cost. So in order to know that, we need to predict how much load the application, how much work the application is going to need in the immediate future. And we need to know how long the application needs this work done, right? And that involves, in the general case, it involves having a crystal ball, which we don't know, which we don't have for the moment. So the best thing we can do is come up with a heuristic, come up with a rule that maybe in most common cases gives us reasonably consistent energy efficient behavior, even though it's not intended as from this part on, this is no longer an optimal solution. I'm no longer going to be talking about achieving the optimal possible energy efficiency, but it's only going to be optimal to the extent that the assumption of this heuristic holds true, which is namely the steady state assumption. Under the assumption that the workload is behaving the same in the immediate future as it was behaving in the immediate past, the behavior of the governor should be optimal. And I mean, this might seem like a strong constraint, but it's one constraint that even Raphael was mentioning in the introduction. So because it kind of underlies almost every frequency governor of CPU FREC right now. So it's not really anything new. However, there is a problem with this heuristic. There is quite some arbitrariness in the definition of what immediate past means. And there is an inherent trade-off between the effectiveness of this heuristic and the reaction time of the heuristic to discontinuous events, like the workload shifting away from steady state or from one steady state to a different steady state, right? So the problem is we need some way of knowing what the right definition is of this immediate past for a given application. And well, also for people that are familiar with the deadline scheduler, so these two parameters might remind of the parameter, the bandwidth parameter of the DL scheduler and the actual deadline parameter. However, assuming we have some way to know what the right latency requirement is of this application, we can easily estimate what the bandwidth requirement is by taking advantage of this steady state assumption, right? So my proposal is to introduce some mechanism for applications to report their latency requirements. So CPU FREC can have a notion of what the right definition is of immediate past. And it can have a notion of how aggressive it can be at rearranging the workload over time in order to optimize energy efficiency without hurting latency sensitive applications, which there are many of them. Passing this information from the application instead of a frequency constraint has a number of advantages, but I don't think I have time to go into them in detail right now.
Right. So we really need to announce a break, and we can go back to this actually at the end of the session because we may have some time.
Let me wrap up with this one slide.
All right.
So actually, I'm gonna go one step forward because the problem with this is that in order for an application to take advantage of, say, this QoS parameter I've proposed that allows somebody to specify this is my late requirement, somebody need to go and fix every user space application out there to take advantage of it. However, in cases, IO devices have some natural latency constraints. Like, for instance, your monitor will have a maximum refresh rate, and if you have an application which has a bottleneck on the graphics on the graphics processor, it's not going to be able to get results out into your screen faster than in a given time frame. So it's kind of useless for CPU Frec to optimize latency beyond a certain level, right? So one of the things I'm trying to do in this series is to instrument the i915 driver for integrated Intel GPUs and have it provide a latency constraint whenever it detects a bottleneck, which is compatible with this optimal energy, power, with achieving this optimal power allocation I was talking about in my slide.
All right, but that's we are over time, really, and then, as I said, that there is some time after the last topic that we may be able to continue this. Let me mention one thing. There was a latency nice concept discussion during the scheduler micro conference a couple of days ago, which kind of relates to this, in my opinion, but maybe not. I may be wrong.
So I think one of the potential ways for CPU Frec to figure out what the latency requirement is of an application is for it to be plumbed through the scheduler. That was one of the slides I had
all
prepared.
right, so
I think there is quite some, you're into something, yeah.
Okay, so let's, if we have some time at the end of the session, let's come back to this. Now we have a break, and we are back at the top of the hour. Yeah, thanks.
Hi, Raphael. Did you get my slides?
Yeah, I've uploaded them. And when
So I only have So I only have 2 slides. So I think it's better for you to share them and.
Oh, I see. Okay, that's fine.
Yeah,
I can do that.
that's very Well, it will be very short unless we find some people that are interested in this topic and have worked with this.
Mm-hmm. There are other, related things, but yeah, let's first focus on this one after the break, though. Oh. All right, coming back. And switching over to the Daniel slides. Daniel, do you want me to make you a presenter or not?
I don't think it works it because there are only 2 slides, and you just switch them for me.
You will tell me when to go to the next one.
Exactly.
All right, that works. Okay, so we can start right now. The floor is yours.
Okay, let me see. Should I share my webcam?
Not necessarily. That, that's fine. I'm not sure if everybody's seeing you, but
okay. So, hello everyone. My name is Daniel. I work at NXP, and mostly concentrated on audio and sound of one firmware. But during enabling this on i.mx boards, I came around to this problem, and now Rafael, can you go to the first slide of the presentation? So basically, with the newest devices, we get that devices partition across multiple power domains. So it's not like in the old case where one device needed just one power domain in order to work. In this case, we have, for example, the DSP needs more than one domain in order to work. I have only found this use case in the kernel in 2 places. One is the NVIDIA Tegra, but I couldn't find the patches for this. This example is mentioned in Ulf's patches, and another board that has the same design is a board from Qualcomm. So I would really like to see if there are any other people working on SoC here who their new designs need multiple power domain to be up in order for one IP to work. Yeah. So in my case here, a device tree node just basically adds a list of handles to the power domains in the power domains handler. There can also be a power domain name field where you can refer these domains by their name. Yeah. Okay, so when I started working on this, and we can go to the next and the last slide. So when I started working on this, I've seen a series of patches from Ulf, which basically adds what I need. That is the multi-PM domains per device. This solution is almost complete, and I had it working on my board, but the problem is that the driver needs to manually attach to all of the power domains. And while this works fine for one driver, and I think I'm the second user of this interface inside the kernel, and this works fine, but now I need to enable another platform which has a similar scenario. And for this new platform, I need to again duplicate the code in the probe function, which basically enables the power domains, and that's not really ideal. Yeah. So my presentation here has more questions than answers. So first question is how should we avoid duplicating the code? And what I've did is I tried to create a helper which basically wraps this functionality, and then each driver just call one function in order for this to work. I have sent this patch, and I have received some some feedback from Ulf, and I think I'm going to the right direction. I think at some point this will be acceptable. But my problem is that this is, and I think this is not good enough. I mean, making each driver being aware that it uses multi-power domains and it needs to call this I call this function multi-power domain attach. I don't think this is the ideal solution. For me, the ideal solution would be for the programmer to just write the power domains inside the device tree, and then after this, everything should just work out of the box. Yeah, so I need to know your opinion on this. Hello, Wolf.
Yes, hello. Yes, I want to add some comments about why it looks like it does today. So we have this legacy problem that earlier we only managed single PM domains cases. And all these cases was done more or less behind driver's back in buses, more or less. So it was quite complicated to make these multi PM domain things happening also behind the back, because it's like two cases were more or less competing with each other. And so the approach was more or less trying to be flexible and give the opportunities to the drivers to do whatever they think makes sense for their particular case.
Oh, okay. But do you see that in the future the solution should be that the drivers should enable the power domains, or perhaps we can do something that the PM core does the power up of the domains?
So I don't have any strong opinions. That's
okay.
The short story. If there is a lot of code that becomes duplicated and open coding is not what we want, of course we should look into it.
So there is another problem, which is obviously that the drivers are not portable then. If you, they need to be complicated to be portable. I mean, additionally complicated, right? Because they need to know which platform they run on, and then depending on something, register the device or assign the device or attach it to multiple power.
Yeah, because
right. So
how is this different from doing the same for clocks or regulators? I mean, the drivers still have to potentially have multiple clocks based on the system they're running at. Regulators don't do that anyway.
That's fair, but then you can describe the clocks in the device tree in such a way that the driver doesn't have to do it, right?
I don't think it's automatically gotten and enabled.
Okay, if not, then this is like another case of an existing problem, right? That device. Right.
They have similar helpers to get bulk clock get, I believe. I don't know about regulators. I think that has it too. But yeah.
So yeah, ideally, if you think about like a really portable driver, ideally it would it wouldn't need to care about what power domains there are in the SoC or in the platform, because the driver basically the driver handles the I/O part, and it doesn't need to know the topology and everything, because if the driver needs to do all of this work, it basically needs to know the topology of the SoC, right? And a board maybe.
That's where the name component comes in, right? So let's say there's another possibility is that power domain, like you have multiple power domains, and only say some of them are needed only when you're running a particular use case. And say in one system, all of these power domains is just like one power domain where you can't control them. In another case, you could have the power domain split up, where you could potentially turn off some of them when you're not running a particular use case. That's where you would use the name to say, hey, like, name the power domains, and then in cases where they're the same power domain, you just happen to have names point to the same power domain.
Yeah, but it boils down to all of that basically. That if the driver really is only used in one SoC, there is not a problem, right?
No, I'm saying even across SoC, you can still have it work correctly. That's what the names are for. So you don't need to know if it's one clock that's say clocking two different frequency domains, or if it's one power domain powering two different frequency domains. You just get them by the name in the system based on how they're actually connected up. That's when the DT, you might have like two entries pointing to the same power domain, for example. So if we go to the DT example, can you go to the slide with the example in DT that you had?
Oh yeah, so I need to switch over to this one. Sorry, because I'm the presenter technically
in this case,
here.
for example, right? Actually, this is a good example. See, in one case, there's a DSP power, then the power for the RAM, and then another for IRQ, whatever, right? So let's say you have a system where the RAM and the DSP are powered using the same power domain. You will just have two entries of, say, power domain DSP and power domain DSP again, pointing to the same power domain, and the driver actually shouldn't care about if it's pointing to the same one or not. They just get the first one is for controlling the DSP.
Yeah, but in that case, you won't be adding both of the domains in the device tree. You will only adding one.
No, I'm saying no. That's you can still. That's the point I'm making. There's no reason to say you only list the DSP thing once. So let's say the DSP and RAM are powered by the same thing. You'll change the second entry to say IMX SC or DSP. You'll remove the underscore RAM part. So from a power domain perspective, it'll turn on the same power domain, but the driver doesn't need to care. The driver will just say, give me the power domain named DSP power control. Give me the power domain named DSP RAM. You don't have to care if it underneath it ends up being the same power domain or not. That's the whole point of the names. You name them by the functionality, not by what it's connected up to.
Perhaps you need a separate device node for the DSP RAM.
Sorry?
Perhaps you need a separate device node that represents the DSP RAM, and then have that point to the DSP RAM power domain. And then, of course, you need some link between both devices.
No, I think that's a different problem. This is an example, right? It could be anything. So I don't think the focus is on whether we need the DSP RAM or not. The point is the driver will be portable by not looking at the actual... The driver shouldn't care what power domain it's attached to. It just needs to say, get me the power domain for DSP, give me the power domain for RAM.
Yeah, so the like generic names, right?
Exactly.
Yeah.
That's why we have power domain names or whatever the other binding was that he was talking about.
Yeah, I've seen those power domain names, and I think that could be an acceptable fix for this. But although I do think that, so for example, how do we work with just a single domain? You just specify the domain here, and that's all. The driver doesn't need to care about it.
Right. If it's a single domain, and let's say in this exact example, in a different SoC, you have only a single power domain.
Yeah.
You just list them 3 times. It'll just work anyway.
Yeah, exactly. But this use case doesn't work when you have multiple power domains.
No. Like I think you're... So your driver should always try to get the power domain for its DSP and its RAM. It should always do the same thing. When it thinks it needs the RAM, it should turn on the power domain. When it doesn't need it,
and it may return the same thing, and the driver can actually then see that this is the same one, right?
Oh, it doesn't even have to. It can just continue operating. It doesn't need to do anything because it's ref counted.
Yeah, but it may not reference count it twice, like, that if this is the same thing, right? Because it may, like, there may be some logic like to power up all of them and so on. So, but that's in the core anyway. Yeah. Okay, that's fair enough.
So the driver doesn't need to actually care whether it happens to be pointing to the same power domain or not.
But yeah, this is a matter of defining the binding. So you can say that if there is one power domain that it stands for all of them, if there are two, then the first one is DSP and the other is for the two other things. And if there are three different, then they are different, right? So
Or I mean, it's a common problem that's even in clocks. Sometimes you have one clock, say, controlling the core and also the bus interface. In some cases, they're independent clocks. So the driver always just gets both the clocks, turns both of them on, and starts running. If they're same clock, it's all represented in DT. So the driver author doesn't need to worry about how the IP is integrated into the system. It's the person who's writing the DT who has to care about it. Hopefully that explains what I'm trying to say.
Okay, I get your point, and I think this could work. But in order to avoid the boilerplate code that we need to write every time in each driver, I think at least we should have some helpers for this.
Yeah, that I agree.
Because
I completely agree.
Because it's not just it's not just simply calling one function. Is getting all the names and then creating some virtual devices and then connecting the virtual devices with the original device. And I think it's better to at least have a helper for that.
I agree.
Yeah, helper functions. I think that's how that seems reasonable. I don't know about the virtual device part, but yeah, seems reasonable to have helper functions.
Okay, Ricardo, do you have any questions or comments? You are in the.
You are online.
It looks like Ricardo is waiting. Ricardo, do you have any comments or questions for this?
No, I do not at the moment.
Okay, so you are just happy. So can you please turn your camera off, like in?
I did the same.
Because this is like confusing a bit. Because if you have a camera on, then people will think that you want to speak.
Okay,
so,
sure.
So yeah. Oh, thank you. All right. So Daniel, you got feedback. I think it was useful. Do you need do you have any more questions or?
No, that's all.
Okay.
I think I also have some feedback from Ulf, which I need to address and resend the next version of the patch. So thank you.
That's good. Does anyone want to add anything to this topic? I think that we can go to the lens topic now, then a few minutes early, and then we can go back to the discussion that we had with Francisco. Does it sound good?
Yeah, sounds good.
Sounds good.
All right, great. So let's do that. So Len, I'm going to give you the presenter's powers now, and you can do whatever you like.
Let's see if that magic button appears. There it is. Let's see, share my entire screen. Let's do that. And now what I'm going to do, actually we have a, let me know if you can see my screen and if you can hear me.
Yes, I can see you and hear you, and I can see your screen.
Okay, great. So I'm Lynn Brown, and I've worked with a bunch of people, a lot of you over the years on lots of things, but what we're going to talk about in this session is suspend resume status, Linux suspend resume status, and we're going to highlight some tools which I've talked about actually last year in this session and in previous years, and very briefly going to go through what they are, because a lot of you have seen them already, but do ask questions if you have them, and then we're going to highlight what's new that wasn't true last year. Okay, so first of all, there's a web page which I'm just going to surf to, because hopefully everything I would talk about is there. If it's not, then we will fix there. And we're going to talk about, I'm going to show you the tools we use, then talk about functional performance and endurance testing. And endurance testing is sort of new in the last couple of years. And so we're getting some interesting results. And so we're going to talk about some of the trends. I'm going to show you some pictures and then maybe brainstorm about what's next, okay? So this is a homepage for PM Graph, which is a project. And what we're going to talk about is the Sleep Graph, which is a tool inside that project. Let me just get right to it. It's very simple to use. You can clone it. You can do a make and run it. Boom. Like in the time I'm talking, you could have run it 3 times. It does have some dependencies. It depends on Python to work optimally. It does need some kernel options, which are built into all but some very unusual kernels, and it will work even without some of the options there. It just can't do everything. If you can't, if tracing's not enabled, it can't trace. Typically what we use for automated testing is we use on Intel machines RTC Wake, and so we will say, but you can also test manual wake up devices, but by default, it assumes you're going to use the RTC wake up in 15 seconds in this example. And then it will output something like this. It'll output it'll output 3 files, an HTML file, and then the backing dmessage and ftrace file. And I'll look at a real example of this so we can scroll around in it. Let's see. For endurance testing, we have some features now that we didn't have years before, and that is if you invoke Sleep Graph, say this way with a multi, this one says do 2000 suspend cycles and don't wait at all in between them. If you could say wait a minute or a second or whatever. This is seconds between them. You can also say 8 hours. I usually run for 8 hours. I just put an 8H here. It will run for 8 hours. And I use RTC Wake too. Actually, I use a patch to sort of hack RTC Wake, so it's sort of hard code to 2 seconds, which is a minimum you can safely set the RTC to, since its actual granularity is 1 second. You can't set it for 1 second because it could fire just as you're setting it. Okay. And then there's a summary. I'm going to show you a real summary in a second. In fact, here's one now. Okay, so tell me, I can't see your hands raised, so somebody tell me in audio if you can see this, or if I can make it bigger and smaller. I tried this. Is it okay? Okay, so this is behind me. I have a laptop, a Dell 9300. It's an Ice Lake 13-inch laptop from Dell. And so this is a output that you will get if you just ran, in this case, it was 8 hours, and there's only 500 tests here because this particular test I put in long delays just to see if it would change some things. Usually it will do about 2,000 tests in that amount of time. And so you can see, each one has a detailed test, but each row is an individual test. It passed or failed. If there was some issue, we highlight that here. This timeout, this is actually benign. Some not helpful person has put the word timeout in dmessage in a normal message, which is really not a nice thing to do. So it throws our tools off, but we'll get that fixed. How long did it take to suspend? Here it took 600 milliseconds. It took about 2 seconds to resume. The worst suspend device was the 915 in this one, and it took entire suspend took 300 milliseconds for that for this device. Coming back PCIe port took a long time, 1.7 seconds, and I'll show you that one. So you can go through and see, and I will highlight some things that pop out from the summary, but if we look at the specific result, this is what a specific result looks like. So, you have your header on the top, suspend time, 1.5 seconds total, resume, 5 seconds. This resume is including Wi-Fi resume, which is not shown here because it's sort of asynchronous, but we actually wait to see how long it takes Wi-Fi to reconnect. this is actually sort of the worst case. This is the first resume of the test. And things actually get faster than this. But here's one. So if you can click on something, if it highlights it fails, it said, oh, PS mouse, this happens on this machine every first suspend this happens. And then it stops happening. So there's some initialization error with the CRIO on the suspend side. But in fact, I think I have some other, like I can go to this guy here, and that's gone. Okay, so here the 915 is the slowest suspend device. This gray bar, oh, so time goes from left to right. These minus things are coming up to the suspend event. This gray bar is while you're suspended. In this case, he was suspended for 30 seconds. That's listed up here. Okay, but of course we don't show 30 seconds, or everything else would be dwarfed by it. So we just put a little gray bar there, and then to the right. Increasing time to the right, and there's 2.1 milliseconds. And Wi-Fi resume here in this example took 110 milliseconds. If we click on this timeout, it's NVMe is the culprit, and it's unfortunately just noise. So if you look at this device, you'd say, well, okay, what I really care about is the resume side of this, and gosh, PCIe port's taking a really long time. And with tracing, we can say where that time went. In this case, it's ACPI PS execute method. Indeed, that method. So it's a PS0, which is an ACPI method to set power on, and you can hover on these, and it shows that we're ending up doing ACPI OS sleep, which are sleeps in the kernel. 15 milliseconds, and then the long M sleep at the end. And so you can strategize for how to alleviate this. There may or may not be something we can do for this. This might be, for example, this might be the implementation of Thunderbolt with probing delays for looking at things on the chain. We may or may not be able to work around this. This is considered slow. A fast system is under 500 milliseconds total, soup to nuts. But this is a problem which is we'll see a lot because this is a very modern machine. This isn't an old machine. This is sort of a new problem. Let's see. Freeze is suspend to idle. Freeze is a synonym for suspend to idle. We could also, I think the examples other examples I showed, you could invent a tool to invoke mem, which on this kind of machine would be an ACPI S3. This particular machine advertises but doesn't actually support ACPI S3. It works, but graphics never comes back. The vendor never intended it to be used, so we've asked Dell to remove it from their BIOS since it's sort of false advertising. And while Windows will never use it, Linux is much more, it will do whatever the user asks them to do. So you sort of have to remove it if you don't want somebody somewhere to use it. Are there any questions about this? Okay. All right, so let's see, we don't need the demessage. And let's go, so what we can do is we can look at, we have a bunch of machines at Intel, both internal and external. These are some of the public machines we have. And across the, we've been taking these measurements for a while. This one, there's some 416 measurements, and then I think that in this one, the latest thing that's run on it is a 5.8.0 result. And so we have a couple of ways to look at this. First of all, what we didn't used to do before, we were happy if a machine could suspend and resume once, then twice was a great milestone. And then it's like, wow, okay, quality will be 10 times. Here we're measuring, if I hover on this one, this is a random machine. So he ran, how many iterations is that? 1,000 iterations, pretty typical. We pretty much run until we run out of time. In this case, he has it might even be some disk results, yeah, which is, we don't test disk that much. Mostly we test freeze, and if freeze isn't supported, we test suspend to ACPI S3. to run for what's 1440 minutes? See here, he only ran 300.
We got interruptions, so we need to repeat
the
last two. You need to repeat the last two sentences because they were not audible. So we got.
That's funny because I was talking about a power or a network outage. Okay, so how apropos. Yeah, so in this case, something, you know, he was doing swimmingly. He was getting 100% of what requested. He was executing, but then something went wrong, probably in the lab this day, and he only did 362. So we don't give him 100% credit. But if we go to the functional tab, we say of the tests that did run, did they function properly?
Changing tabs, we're not able to see it.
Okay, so it should be pretty subtle. It's actually not a tab. So this graph is flat. Do you see a flat graph here at 100%?
Yeah.
Okay, then it changed and you blinked. You blinked too slowly. So here we have a spike on the endurance where he did not complete these tests, so we didn't give him credit. So this is the first thing. The most important thing about suspend resume is that it actually works. If I'm a customer and I use suspend and I say suspend, I don't check that it worked. I put it in my laptop. I put my laptop into my bag. I zip it up. It's sealed. If that thing's running, it's going to cook, and I'm going to open it up and it's either going to overheat or its battery will be dead or both. So it really has to work. So it's a big deal if suspend doesn't follow through with what the user asked. But for the ones that didn't fail for some lab reason, in this case, this guy's got a really great record. This was 5.4.0, and he's doing very well. Now, there's other machines that don't. So if we could scroll down, like let's say we go look at some of these Dell machines, like I don't know, 5510. So here what we do is we found that in 5.1 RC2 there was some regression where this guy ran but he failed. Okay, and I think I can't remember what happened in 5.1, but we may have bisected hardware configuration issue, which happens from time to time when you've got 100 machines. Sometimes somebody will stick something in or take something out, and then you've got to say, why did it start failing? You got to figure out why and fix it. Let's see. I think the 9300's on here. So if I go 9300, yeah. So this is the machine we're just looking at, for example. And here, this was pretty recently in 5.6. In 5.7 RC1, there was a regression, and suspend only worked half the time. And it turned out it was Bluetooth. Bluetooth started to fail randomly, and to make compound take the prerogative of refusing for the system to suspend. That's very bad hygiene, particularly, again, if you're in that laptop case overheating. Thank you very much. You just destroyed my laptop Bluetooth. And it took a couple of RCs till we bisected this, and then it went away, and today we don't have this problem. And so we can identify trends with this system. But this system is only as good as the machines that we're testing on. So, I noticed this. I actually have this machine right next to me. It looks like in the lab there's another one with a different name. But what we really need is more people using this tool and reporting bugs. And so to that end, we have been in to say about running this tool in their labs. Indeed, the vision would be that there would be an opt-in for end users, because what we really want to do is cast a very broad net to run on many machines, as opposed to I can run 15,000 cycles on my machine right here, but really what I want is 10 cycles on 150 machines or 1,500 machines, right? And that will prevent Linux from, like this might
At least it's not Bluetooth that's failing now.
Yeah.
SRIX?
So we get really bad network cuts for you. I mean, the last part was not audible at all.
Did we lose audio? Okay, what's the last thing I said?
Not just audio, video too. I mean, can you switch the camera off? Maybe that may help. Slightly.
Let's see. Yeah, sure. Yeah, you don't really need to see me, right? Camera off. Okay. Okay. So can you see my screen?
Yes, we can.
Okay, so that's, I don't know, I need my screen and I need my voice. Everything else is optional. This machine, so SRIX is an SoC-wide sleep state on Intel hardware, so you go into the deepest CPU idle state, and if other devices are down, the entire SoC can turn off power rails and what have you. And this particular machine used to get it 100% in 100% of the measurements, and then it broke. And I don't actually know the story for this machine. It could have been a configuration change, or it could have been a BIOS change. Here's another one where it broke, and then it got better. So we track this, but we also track performance. So here, for example, random machine, this ASUS, whatever this machine is, it was resuming in about 2 seconds, and then something happened in 4.19, and now it's resuming in about 1 second. Cherry trail. And so these move around, and we can track them and recognize regressions. The Apple ones are pretty flaky. They jump all over. Let me make sure I'm on public machines. Yeah, public. Okay. And so if we look at, say, the Dell 9300, we're just looking at, there's a lot of Dell machines in here. Yeah, I don't know why this one went down to 374 milliseconds. Change. But we do have machines. I think the first time I did a suspend resume talk, I showed a machine that could resume in 10 milliseconds.
Okay, did we lose land entirely? So?
Looks like it.
Yeah, right. Okay. Let's give him a couple of minutes more, and then we'll.
Looks like his download speed is okay, but his upload is busted, I think. You can hear us apparently.
Right. So this is a so okay. What did you say? I didn't understand entirely. So
he's able to hear us apparently, but we can't hear him or see his actions.
Oh, I see. Solan is saying that he's okay because I'm trying to work on the notes, so so I don't see the public chat.
Okay, something changed. Oh.
Unmute. Hello, can you hear me now? I seem to have gone on to mute.
Yeah, we can hear you. Yes.
Back in, I think maybe the network dropped, and then I had to repress these buttons to make it come back.
Probably yes.
Okay. So give me some chatter so I know you're still there. Like say yes, or you're an idiot, or something.
Yeah,
like that.
we are still here. Yes.
Okay. So one thing we can do is we can scrape. I was just showing you some graphs, but we can also scrape. We've got a machine.
No audio again.
Yeah, we lost him again. I think, yeah.
So sharing the screen is basically not working. I guess it would be better than if you can hear us. It would be better if you just switched over to no screen sharing and just talking. I believe. Oh yeah, that okay. I will take the presenter, and now I will bring the default. Maybe not. Intro. By the so Len, are you with us? Okay, so that's hard. I mean, the land still has a right. I'm talking about a Peter's discount. So Len technically had had 5 minutes more for his topic still, but because of the network issue, I think we can switch over to the or switch back to the one regarding the CPUs and CPU energy efficiency. Let's just call it this way. So
sounds fine with me. We can switch back to Len's discussion once he comes back.
Right, that we can do that. Let's say I will make you a presenter again, Francisco, so you can let me bring up your presentation again.
Good.
This would
by the way, I cannot see the PDF on the agenda yet. On the
oh yeah, because I will add the slide decks to the to the main site later. I was just uploading them into the Big Blue Button system now, so that your slides are up, and then they will be there. No worries.
Cool.
Cisco, yeah. Let me make you a presenter, and off you go.
All right. So where were we at?
At the here, I think we can start
right.
over from this point. Yeah. So,
right. So.
Oh, okay.
So I guess
let me just for the the kind of janitorial things, like we are going to stop at the top of the hour, if that's fine with everybody.
Sure. So I guess when we ended, I was just discussing this proposal about giving applications some way to explicitly state what their latency requirements are, because that tells CPU Frec how aggressive it can actually be about improving energy efficiency, right? And there is it also removes the burden of having to estimate the bandwidth requirements out of the application, which can be complicated and has the potential, if done naively, it has the potential for one application to affect the behavior of other applications running on the same processor. In the case where assuming, for instance, that an application was using frequency QoS constraints, there will be some potential for the application to set a frequency which is good enough for the application and energy efficient, but which might affect the performance of other applications which just happen to be scheduled to the same core. So I think there is some merit in having some central entity controlling the frequency of its CPU, which can use latency requests coming in from applications as a guide. And there are some ways for us to plumb these latency constraints through, but I also wanted to show you this graph, which is it's taken from by using ftrace. This is a graphics application from a synthetic benchmark, and you can see the behavior of the application before using my governor and after. And so in this case, I haven't actually fixed the benchmark. I haven't actually changed anything in the benchmark. As I was saying, I've also instrumented the graphics driver to provide a latency target as soon as it determines that the GPU is a bottleneck for this application. And as you can see on the graph afterwards, there is still quite some frequency oscillation. I don't know if you can see this clearly enough. Assuming you have the PDF, you could just zoom in because it's a vector graph. You can see that the orange line is the frequency the CPU is running at whenever it's active, and as you can see, there is quite some oscillation during startup. And as soon as the GPU gets backed up and becomes a bottleneck, it provides a latency target for CPU frec, and then CPU frec manages to find the one frequency which is allowing it to average the same performance as before. As you can see, the blue line, well, the blue line is the average performance of a given processor, and as you can see, it's even averaging a slightly better performance because while doing this, it's giving back some of the TDP budget to the GPU, which is the one there is about actually, right? And I have some benchmark results in one of the other slides. Actually, I can jump to that.
So actually, I would rather talk about what changes you're proposing, because you are talking a lot about the motivation and about the theory behind those things and so on, and we have just a little time to see what the proposal really is, which is the point of the whole session, by the way. So.
Let's talk about the plumbing then. So yeah, indeed, this is probably the most appropriate slide for this conference, right? So there are several ways how an application could get this information, these latency constraints, all the way to CPU frec, and this is also the same mechanism I'm using from the graphics driver in order to provide a latency target, which is guessed by the driver, assuming that the application doesn't provide a more strict one. And my initial approach was to implement a custom CPU frec interface, but there was some opposition to this. So in the current V2 of my series, which is the one on the mailing list right now, I tried to take advantage of PMQoS constraints. So the current interface is using PMQoS. However, it's not exposed to user space yet, but it will make sense to do that eventually. However, I think ideally the schedule, ideally, as we were discussing before, it will be beneficial to give the scheduler control of this and give this similar treatment to the utilization monitoring, which is done at scheduling level, because that will allow us to get a more optimal response in cases where, say, an application which has a specific latency constraint is shifted from one processor to another, and it will improve the isolation between applications. So in general, multitasking cases are handled in a kind of graceful way by my current PMQS implementation, but it could be made even more energy efficient if we get some help from the scheduler, because the way it works now, and actually we can see that in this one slide. So right now, the device driver provides a certain latency constraint, which is global, because the PMQS mechanism I'm using is necessarily global for the host system. We could make it CPU specific, but that will create a series of other problems. So I think we either want a global PMQS constraint, kind of like the CPU DMA latency stuff, or we want it to be scheduling aware, because assuming we had something CPU specific, it will be kind of difficult for the application to get this effect consistently, since the application, unless it has set some specific CPU affinity that we don't want to force all applications to do, has no control over which CPU it's ending up in. So
okay, question at this point, like,
yes.
so the QoS really, or whatever interface in this
Yes.
role basically tells you how much performance the application. Oh yeah, Peter is saying that global state is fail. Yeah, I
Right.
agree.
I agree.
Okay.
I agree that we can do better than a global constraint.
Yeah. Okay.
However,
So, but
it will
let me
involve
ask.
getting.
Let me ask the
I fully
question
agree
though.
with him.
Let
Yes.
me ask the question though. The question is that this basically the QoS is a way for the application to say or specify how much performance it wants, right?
No, not exactly. It's not a performance control. It's a latency control. Okay, so the
Okay,
application is saying,
latency.
I don't know how much bandwidth, I don't know how much performance I want
Right,
on the
but
average out of the
no.
processor. Please get
So,
it for me. But
so Francisco, let
yes.
us agree on terminology in the first place, okay? So latency is part of performance.
Sure, but there is a subtlety there. It's not throughput, which the application is constraining directly. It's
Okay.
the time scale at which it wants its throughput to change, assuming there is a discontinuous event.
So this is a very complicated notion for application writers to understand.
I don't think so. I think it's actually simpler for the applications to control this than controlling the raw frequency or controlling the raw performance. Because,
yeah, so they cannot do that. But I'm saying that how
it's simply a reaction time. Okay, and applications have, I think, a much easier way to decide what their latency constraint is than what their megahertz performance
yeah, that's
should
true.
be.
Obviously, yeah, that I agree with. But then
Because
that from the application writer's perspective, that would be the max. So this would be the maximum reaction time they expect, or the minimum, or the something else.
Maximum they can tolerate, I believe.
Sorry.
Responding to Rafael's question, I think this is the maximum latency that they would be able to tolerate. Would be my
tolerate,
answer.
yeah. So they are willing to tolerate. Okay, that's okay. Okay, so let's go ahead.
All right. So this is how the plumbing will look like with the current PMQS based solution, which I know it's not ideal. I know ideally we want this to be tracked per scheduling entity, just like PELT. However, it allows us to achieve pretty much the same energy efficiency and the same performance as the scheduling-based solution, and it's massively simpler. So I think there is some benefit from going for this solution as initial approximation to it. Well, in some cases, like primarily cases where the application, or there are multiple applications running in parallel on the same system, it's possible for one application to set a latency constraint which is incompatible with another applications, and in that case, what this is trying to show to you is that the most strict constraint is the one that's going to apply, and so that means that the application which has the least strict requirement on latency is going to behave as if the most strict latency requirement was being used, which is going to be energy inefficient for it. So that's the main limitation of the global approach. And,
all right. Okay. So we have 5 minutes. Okay. So I think that we agree that this maximum response, maximum expected response time, or latency tolerance, quote unquote, right, is something that makes sense. And how do you expect the governor to react to this?
So it's fairly straightforward. Right now the governor is basically using a low pass filter, which is controlled by the latency parameter, which is coming in through this interface, whichever it is. And as you can see, the waveform of the CPU frequency is filtered according to this time parameter, which is it can be adjusted dynamically.
Okay. No, okay, go ahead, Srinivas. Go ahead.
When you say application, are you specifying MISA or some applications to specify latency constraint, or your application is like you are doing it based on stats in your i9 driver, but it's not like application is driving your stuff, right?
Not right now, but it will make sense. I think it will make sense to expose this control to user space, but I haven't done it in my initial series because surely enough, exposing some interface to user space is like engraving it into stone, so we won't be able to change it later. So I'm trying to keep things local to kernel mode for the moment. However, in many cases, it might be possible for the user space application to have a better idea of what the optimal latency target is, instead of the device driver having to guess it.
So your draw operation happens on some specific application context, right? In devices, it's not like, do you know you can easily identify those threads, right? Which are actually driving the graphics.
So sure. Well, with the current approach, because it's something which is only ever, this latency target is only ever set by the kernel itself. It's based on the kernel device driver identifying which user space application has a bottleneck on it. And actually, this is not necessary in V2, but it is necessary in the scheduling-based prototype I also have in the works. And it's fairly straightforward, because in order to detect a bottleneck, we simply figure out when this GPU or whatever IO device becomes overutilized, and at some point the CPU thread interacting with that device ends up blocking on that device. If there is no blocking, there is also no need to constrain the CPU frequency, right? Because if there is no blocking, that means the CPU thread is basically independent. So we are only interested in limiting the performance of CPU threads which are dependent on the result from some IO device. And that's something, yes, we can find out easily from kernel mode. And then this information is communicated to the scheduler by providing it a frequency target, which if one of the, I think, most compelling...
There are a few things which I can agree with here, and there are a few which I don't. So For example, it is like you can the whole manipulation of the frequency. I don't know why do you want to give the scheduler a frequency target. The scheduler should be able to figure it out.
A latency target. A latency.
Latency. Oh, okay. So you said frequency.
Sorry for that.
That was confusing. Okay, so a latency target. Okay, that's that. My point is that it may or may not be a latency target. It may be something else, which
frequency and latency target. I use frequency target. I use the word frequency target.
Frequency target is worse than latency. Latency is better.
They are equivalent. I mean, for me, a frequency is just the inverse of a time parameter.
But then as I said, to the application developers, it is much. I mean, the frequency, as you said yourself, is difficult to handle, like, because if you are an application writer, how would you know the frequency of the target system this application is going to run on, right? This is like something completely abstract, but you can specify your latency tolerance for various things, right?
Yeah, that's what I'm trying to do.
Right. So okay,
however, there is a subtlety here. Actually, in my current PMQS interface, this latency target is exposed as a frequency target, which is just the inverse of the latency target the application wants to specify. But that's kind of a technicality, which is
yes, it is a technicality. So I'm still trying to, avoid getting too much into those technicalities, like at this level of discussion, because I would like us to come up with a general picture of what we want to do, and maybe there are alternative ways to implement certain things which should not like influence the general idea too much, right? Because then so I would like to get to the like general picture of what is. I think we understand what is needed. We understand on what the problem is and what you want to achieve, and now we are talking about some ways to do that, but I would like to stay at the possibly general level until we get very much into detail, because
so do you have some specific proposal which is not on this list?
I was thinking about certain things, but I still need to, before I say what I think in particular, I think in the first place, I think that this is really this is really something that you need to do on a per task basis, because if the code that the CPU is running is not related to your whatever device has a problem, then manipulating the CPU frequency doesn't help, right? If the task is completely unrelated to the device, so you need to say which tasks are affected in the first place, right?
Right.
Which means that you need a per task interface.
However, with the current global interface, the global CPU frequency governor is still going to take the most strict constraint out of all the applications running in a single RQ, which means that even if there are multiple applications which have conflicting requirements, the CPU governor is going to take the most strict one, which it's energy inefficient, but it's not going to decrease the performance
let me say something. It matters what task is currently running. I mean, what task is picked up by the scheduler to run on the CPU, right? Because this is what matters. Right? So if this task has a certain requirement, then you need to use the requirement of this task, nothing else. That's it. Right? So,
the price for not doing that, the price for not going all the way to a scheduling based plumbing, means that applications which are having a device, an IO device bottleneck, and are running on the same CPU concurrently with other applications which don't have a bottleneck and are actually possibly latency bound, we are simply not going to get this optimization kicking.
Maybe
but
not.
It's not it's not a catastrophic failure mode.
Okay, so we are off like by a few minutes already over time, so the session is over. We are in the anyway, beer above time.
I agree.
Peter said. So let us continue, and we can do that on the mailing list, and we can do that. We can talk to each other in real time also.
Anyway, I agree with you. I agree with the point that ideally this will be something we keep track of as a sort of scheduling entity, but parameter, surely enough.
Right. So this is one point that I have. I may have more when I digest all that.
However, do you think it's worth setting the requirement of this being scheduling based from the start? Don't you think it will make sense to get the governor reviewed and in good shape? And given that
so if this is where we want to get eventually, then we should try to get it from the start.
Sure.
Because,
and actually, I have some code already which is scheduling based. But it doesn't. We still need to decide what kind of interface we want for applications.
And also, how. First of all, we need to agree, and we not just between the two of us or two of us and three of us, but also with Peter Z and other people on how on what the interface will be. Or we want to be there. What input the scheduler will get from where? From the driver or from the application itself, and how we want the scheduler to act on that input.
Right.
And we have to agree on that without going into detail and coding anything. Still. Coding is great for a proof of concept, like for but the idea of what we want to do needs to be independent of that.
Sure.
Right, and that's what I would like to get from all of this discussion. The idea of what we want to go, what we want to do at a very generic level or general level. As I said, first of all, what the input will be there for the scheduler, how you want it to consume it, and who is going to provide that input and in what way, and and all of that needs to be agreed on.
Sure.
And then we can implement things.
Sounds good. So let's talk on the mailing list about this.
Right. And thank you.
Preferably profile some application tasks which you have and show those that we can see which applications are actually causing these things. Some profile graphs.
Sure. So actually, I have a small subset of applications which have some serious energy efficiency improvement here.
There are applications. They are, when I say applications, I don't mean benchmarks. I'm saying what threads in the user space are actually causing these issues. Then we can profile that.
So understanding of what's going on at the low level. I mean, in terms of interactions between various threads and CPUs and GPU and so on would be awesome to have.
Sure, that's all what I was trying to talk about on this presentation.
Yeah, but this is
that's why we kind of got lost into so many generalities. I was trying to describe the details of the energy efficiency problem.
But if you come up with an example and say in this workload, this is what's going on, right, in detail.
I had such an example.
Great. Okay. This is
the effect, right? I'm saying what's caused it, right? Like suppose you are running this benchmark 5 threads are talking to each other, they are bouncing on each other, something like that. Why it's happening, right? This is an effect because of some application. This is the ultimate thing happened because of some higher level things, right?
There are interactions involved, and Srinivas would like to understand what those interactions are.
Yeah.
Okay, but
really,
is there,
like
so in this case, for instance, in this one example I was showing to you, what is happening is the application is rushing to prepare some work for the GPU to render, and then it is submitting it to the GPU, and then it's attempting to display the results on screen, and then it blocks on the GPU actually completing that work, and then it idles for a significant fraction of its CPU time. And then at some point, the GPU is done with this bit of work, and the CPU gets unblocked, and then it rushes again. Then it gets a new burst of work, and that leads to great oscillation.
Okay, so this is one detail that I'm kind of missing. Is the application or is the thread talking to the CPU actually sleeping at this point? I mean, it's like
it periodically sleeps on the device driver because it has a bottleneck on it. It has a bottleneck, right?
All right.
However, and what I want to
it's
achieve,
woken up and it goes, okay, good. So this is one thing that, yeah.
And what I want to achieve, is attempt to obtain the same average performance out of the CPU, which keeps the GPU 100% utilized, but while investing the minimum possible amount of energy. Because actually, in this specific case, as you can see, the average performance also increases as a result, because this releases slightly more TDP budget to the application for the GPU.
So now something for me to understand, and I'm not claiming to understand it right now, is if the application is sleeping, why doesn't the utilization of it drop? And so why doesn't the frequency?
Sorry, the utilization? What do you mean by utilization? Do you mean the busy fraction, like the fraction of time which the CPU is busy? This is this green line here, and as you can see, it's pretty low. It's like on the before case, the application is pretty much sleeping most of the CPU time, and then whenever the CPU.
Okay, so as I said, I need to understand this picture, okay, because I don't right now, honestly.
Feel free to take your time and zoom into the PDF so you can see the details.
One thing that, okay. So we are over. Okay, so let's continue in the mailing list in whatever ways we can talk to each other. That's an important problem to address. I think that you have good ideas about how to do it, but we need to all of us need to understand the picture that you have and agree on something. Okay, so let's continue this.
Yeah, I hope this presentation helped some in order to achieve some understanding.
Right. Thank you. Yes, it was useful. So thank everybody who contributed to this micro conference. I also would like to thank to our sponsors and the organizing committee of the conference for allowing us to participate in it. And I think that hopefully the discussions here were useful for everybody, and they were certainly useful for me. We have some shared notes. I would like to have more, but then that's how it goes. So thanks a lot, everybody, again, and we'll see you on the mailing list and in conferences. Hopefully, not in the virtual form next year. And so thank you very much. And I should actually go to the next slide. Yeah, many thanks to the sponsors of the LPC, and thank you for everybody who participated in this. Yeah, see you next time.
Thanks, Rafael, for organizing it. Thank you.
Yeah, you're welcome. Thanks. It was a pleasure. Thank you.